Fakultas MIPA merupakan salah satu fakultas yang berada di Universitas yang beranggotakan 5 jurusan, yakni jurusan Matematika, Statistika, Fisika, Biologi, dan jurusan Kimia. Sebagai salah satu jurusan yang berada di bawah naungan Fakultas MIPA, jurusan Kimia telah berdiri sejak tahun 1987 dengan membuka program studi sarjana kimia. Hingga tahun 2020 ini, jurusan Kimia telah mengabdikan dirinya selama 33 tahun. Dalam kurun waktu tersebut, jurusan Kimia telah berproses dan berhasil mengembangkan diri, sehingga saat ini memiliki 3 program studi, yaitu program studi sarjana kimia yang telah mendapatkan peringkat A oleh Badan Akreditasi Nasional Perguruan Tinggi atau BANPT, dan program pasca sarjana yang terdiri dari program studi magister kimia dan doktor kimia.
Nama saya Dr. Mas Andi, saya Ketua Jurusan Kimia. Jurusan Kimia mempunyai visi pendidikan dan riset kimia dalam mengembangkan sumber daya alam yang berwawasan lingkungan. Jurusan kimia juga mempunyai misi, ada 3 misi yang diemban dari visi tersebut. Yaitu yang pertama adalah misi pendidikan untuk menghasilkan lulusan pendidikan kimia yang profesional dan diakui oleh masyarakat nasional maupun internasional. Misi dalam mengembangkan riset-riset yang berbasis pada alam lokal untuk menjadi unggulan. Yang ketiga adalah mengimplementasikan hasil-hasil riset yang dapat digunakan untuk industri yang
Perkenalkan, nama saya Dr. Wulandari. Di sini saya selaku staf pengajar dosen di jurusan Kimia Universitas Brawijaya. Jurusan Kimia Universitas Brawijaya telah memiliki sumber daya manusia serta pengajar dosen yang sangat profesional dan kompeten di bidangnya masing-masing. Mayoritas dosen di jurusan Kimia Universitas Brawijaya adalah doktor dan profesor. Selain itu, dosen-dosen di sini juga berasal dari universitas ternama baik di dalam maupun di luar negeri. Jepang, Jerman, dan Australia. Staf pengajar dosen juga telah memiliki riset pengembangan yang terarah, sehingga dapat memberikan fasilitas yang memadai bagi mahasiswa untuk mengembangkan pendidikannya. Ada berbagai macam divisi seperti LBI, LBO, dan lain sebagainya. Kemudian untuk divisi fakultas, eksekutif mahasiswa, badan legislatif dengan nama DPM, dan LOF yang banyak sekali menampung minat dan bakat dari mahasiswanya. Kemudian untuk di tingkat universitas sendiri, terdapat banyak sekali organisasi seperti EM, UKM, dan lain sebagainya, sehingga untuk minat bakat dari setiap mahasiswa itu dapat terwadai baik di lingkungan jurusan
fakultas, dan universitas.
Pada saat kita belajar di dalam kelas, kita tidak hanya mengetahui ilmu-ilmu yang kita dapatkan, tetapi kita bisa mengeksperimenkan atau mengimplementasikan ilmu-ilmu yang kita dapatkan di laboratorium. Jurusan kimia sendiri memiliki berbagai macam laboratorium yang didukung dengan berbagai macam instrumen-instrumen yang sangat baik. Seperti contohnya ada laboratorium biokimia, laboratorium fisik, kemudian laboratorium anorganik, analitik, dan juga organik. Kita semua tidak khawatir bagaimana prospek kerja pada saat lulus berkuliah. Buat teman-teman semua, jangan khawatir. Karena pada saat lulus berkuliah dari jurusan kimia Universitas Brawijaya, banyak prospek-prospek yang ditawarkan, seperti pada industri makanan, farmasi, ataupun industri yang lainnya, dengan berbagai macam posisi seperti quality assurance, quality control, research and development, kemudian analis laboratorium.
Saya Zubaidah Ningsih AS selaku Koordinator Kemahasiswaan dan alumni di jurusan Kimia FTP MIPA Universitas Brawijaya. Tanggung jawab yang saya lakukan adalah untuk meningkatkan suasana akademik di jurusan kimia. Suasana akademik ini bertujuan untuk meningkatkan interaksi antara dosen dan mahasiswa di luar kegiatan perkuliahan. Kegiatan-kegiatan yang dilakukan untuk meningkatkan suasana akademik ini diantaranya adalah penelitian yang dilakukan oleh dosen dan mahasiswa, kemudian juga pengembangan program kreativitas mahasiswa, baik di level dalam negeri maupun luar negeri. Juga ada KKN tematik, di mana mahasiswa bekerjasama dengan dosen mengaplikasikan hasil-hasil riset di masyarakat umum. Yang keempat juga ada forum ilmiah jurusan kimia, di mana forum ini dilaksanakan tiap minggu, yang mewadahi diskusi maupun interaksi antara dosen dan mahasiswa dalam membahas sebuah tema tertentu. Yang kelima adalah pelatihan dan kuliah tamu, baik dari dosen, alumni, praktisi, maupun tamu yang lain, baik dari dalam maupun dari luar negeri. Sebagai luaran dari kegiatan peningkatan suasana akademik, banyak dilakukan kegiatan-kegiatan untuk melakukan publikasi, baik yang dilakukan oleh dosen maupun mahasiswa.
Mari kembangkan potensi dan kompetensi Anda dengan bergabung bersama kami di jurusan Kimia Fakultas MIPA Universitas Brawijaya. Join UB, be the best! Fakultas MIPA merupakan fakultas yang berada di Universitas Brawijaya yang beranggotakan 5 jurusan, yakni jurusan Matematika, Statistika, Fisika, Biologi, dan jurusan Kimia. Sebagai salah satu jurusan yang berada di bawah naungan Fakultas MIPA, jurusan Kimia telah berdiri sejak tahun 1987 dengan membuka program studi sarjana kimia. Hingga tahun 2020 ini, jurusan Kimia telah mengabdikan dirinya selama 33 tahun. Dalam kurun waktu tersebut, jurusan Kimia telah berproses dan berhasil mengembangkan diri, sehingga saat ini memiliki 3 program studi, yaitu program studi sarjana kimia yang telah mendapatkan peringkat A oleh Badan Akreditasi Nasional Perguruan Tinggi atau BANPT, dan program pasca sarjana yang terdiri dari program studi magister kimia dan doktor kimia.
Nama saya Dr. Mas Rudi, saya Ketua Jurusan Kimia Universitas Brawijaya. Jurusan Kimia mempunyai visi menjadi lembaga terkemuka di bidang pendidikan dan riset kimia yang berwawasan lingkungan, riset pendidikan dan riset kimia dalam mengembangkan sumber daya alam yang berwawasan lingkungan. Jurusan Kimia juga mempunyai misi, ada 3 misi yang diemban dari visi tersebut, yaitu yang pertama adalah misi pendidikan untuk menghasilkan lulusan bidang kimia yang profesional dan diakui oleh masyarakat nasional maupun internasional. Misi dalam mengembangkan
Okay, good morning, ladies and gentlemen. Welcome to the Symposium on Organic and Applied Chemistry 2021. My name is Ania Shakila, and I'll be your host for today's symposium. First of all, I would like to say thank you very much for all the participants that has registered and joining today's symposium from Japan, from Indonesia, from Gambia, and maybe there are participants that also came from other countries. Thank you very much, and please enjoy yourself. Today's symposium is aimed to promote mutual exchange between scientists and experts across the nations to disseminate their research findings, discuss innovative ideas to tackle the contemporary problems, and encourage their collaborations. The symposium is organized in conjunction with the 3rd Joint Student Symposium between Brawijaya University, Osaka University, Okayama University, and Ritsumeikan University. This meeting is expected to provide an opportunity for young scientists to communicate with the senior scientists and widen their perspective through discussion with their peers across the nation borders. Today's symposium will be divided into 2 sessions with 10 minutes break in between, which the first session will be the keynote speakers' presentations. That we will have the first keynote speaker is Professor Hideki Okamoto. The second keynote speaker will be Professor Hidehiro Sakurai. The third keynote speaker will be Professor Mikio Nishizawa. And the fourth speaker will be Professor Warsito. And for our second sessions, which is our student oral presentations, the first one will be Andrian Sucahyo. The second one will be Tatsuki Sato. The third one will be Aoi Tatsuki. The fourth one will be Butsaratip Suwatananuru. And the fifth one will be Momodo Saliso. So, second of all, I would like to inform for all the participants to please keep the microphone muted during the lecture. And if you have any kind of questions or opinions, please do not hesitate to raise your hand and the moderators will choose you to deliver your speech. Or you will also always be able to write your questions or opinions through the chat rooms. So, ladies and gentlemen, before we start our first sessions today, we will first hear the speech from the Chief Committee of today's symposium and also from the Dean of Mathematics and Science, Natural Science Faculty from Brawijaya University. The first speech will be delivered by the Chief of Committee of today's symposium, Mrs. Siti Maria Ulfa, Doctor of Science. Please, time is yours.
Thank you very much, Ania. Thank you very much for all the audience. Thank you very much for Pak Widodo as the Dean of Faculty of Science. I will, on behalf of organizing committee, I would like to welcome all of you, the keynote speaker, I saw Professor Hideki Okamoto and also Professor Sakurai as a keynote speaker in this event, and all the invited speakers. I saw in here Mamodu, Andrian, and all the distinguished guests and participants in the symposium on organic and applied chemistry. Welcome all of you. Actually, this is the first symposium organized by Laboratory of Organic Chemistry, Brawijaya University, Indonesia. In this symposium is organized in conjunction with the third Joint Student Symposium between Brawijaya University, Okayama University, Ritsumeikan University, and also Osaka University. This meeting is expected to provide an opportunity for young scientists to communicate with the senior scientists and widen their perspective through discussion with their peers across the nation. So in this session, around 150 people registered in this symposium, consists of 4 keynote speakers, 5 oral presenters, and the other is non-presenter participants. And last but not least, I would like to thank all of the conference participants who will contribute to making this event the most memorable events. And then let's enjoy the symposium and the discussion. Thank you very much for the time.
Thank you very much, Mrs. Di Maria Ulfa, Doctor of Science, for the speech. And for the second speech, please welcome the Dean of Mathematics and Natural Sciences Faculty from Brawijaya University, Professor Widodo, Doctor of Philosophy in Medical Science. Time is yours.
Thank you for the MC, for the time. Assalamualaikum warahmatullahi wabarakatuh. First, let us express our gratitude to the merciful God who has granted us with blessing the grace that we could gather here today to attend International Virtual Symposium on Organic and Applied Chemistry 2021 in conjunction with the third Joint Student Symposium. Ladies and gentlemen, respectable keynote speaker, presenters, and committee, first of all, I thanks to Dr. Maria Ulfa as chairman, and also thanks to the Dr. Poncho as head of the chemistry department for arranging this wonderful events to open horizon for our students to understanding new finding and innovations from the first hands of prominent scientists. Also, this event I think is really important also to strengthen our networks and also international collaborations. Furthermore, I would like to express my sincere gratitude to the speaker who joined us to share their year's knowledge and expertise, to Professor Mikio Nishizawa from the Ritsumeikan University, Professor Hideki Okamoto from Okayama University, Professor Hidehiro Sakurai from Osaka University, and Professor Warsito from the Brawijaya University. And also I would like thanks to all of the presenters. And also I think here I would like to give the report to especially our collaborator, Nishizawa Sensei, Okamoto Sensei, and Sakurai Sensei, that Brawijaya University already appointed by the governments to be autonomous university. I think with these conditions, so Brawijaya University maybe will already more flexible to develop academic regulations and also international collaborations. And also, this is also opportunity for us, Brawijaya University, with this new status. So maybe have more fun for the research from the governments. But with this condition also, yeah, we also got a very heavy target, I think, from the government to accelerate the research especially to achieve the research product, innovation, and also the internationalizations. Therefore, I do help from you to strengthen our collaborations, especially to increase, to enhance our university to be world-class university in terms of the research and educations. In this occasion also, I propose to Ritsumeikan University, Okayama University, and Osaka University for possible establishing joint lectures, either in the normal semester or summer course. I think this program, the joint lectures, is very important for our students, especially to open knowledge and also to share the culture between Indonesia and Japan. And with this program, I think I hope that our students and also maybe the student from Japanese university may take class or maybe take credits. And then with this condition, I think they're more beneficial for our university, of course, with Japanese and also Indonesian students to enhance the understanding in culture, and also international environments, especially Indonesia and Japan. And also, I think in this occasion, I would like to give most profound appreciation to students who present this research today. There is some, I think, some students, they are Tatsuki Sato, Aoki Tatsuki, Putsaratip, Suwatana Luruk, Adrian Sucahyo, and Momodu Silao Sue. I'm sorry to maybe wrong the pronunciation of your names. And also I think all of the participants today for your effort to activate the science forums. I think this is very, very good and very useful for our institutions, especially Brawijaya University, to enlarge the collaboration and network for the international community. And finally, in anticipate of fruitful and meaningful seminars, I am as Dean, the Faculty of Mathematics and Natural Sciences, officially open the International Virtual Symposium on Organics and Applied Chemistry 2021 in conjunction with the third Joint Student Symposium. I wish you enjoyable talk and thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, thank you, Professor Widodo, for the speech and also for the opening remarks. Ladies and gentlemen, before we start the first sessions today of the keynote speakers, to perpetuate today's memorable symposium, please, I would like to ask you all to activate or to open your camera, and we will have a little photo sessions for today. Please, everyone that is able to open or activate the camera, we'll have a little photo sessions today. Thank you very much for all the participants that already opened the camera. I'll count from 1 to 3 and I'll screen capture for the first gallery. 1, 2, 3. And for the second page, please 1, 2, 3. And for the third page, please 1, 2, 3. Okay, thank you very much for all the participants. And this is the time for the real deal. We will have our first sessions today. And the first session will be led by our beautiful moderators, Mrs. Anna Savitri, Doctor of Philosophy. I put my trust on you. Please, time is yours.
Okay, thank you, Sania, for the introduction. Good morning, everyone. My name is Ana Safitri. I'm also from Chemistry Department. Today I will be the moderator for the first session. For this morning, we already have 4 keynote speakers. For the first keynote speakers, we will have Professor Hideki Okamoto from Department of Chemistry, Okayama University, Japan. The presentation title of Professor Okamoto will be Fluorescence Manipulation of Amino and Amido Substituted Phthalimides, sorry if I pronounce it wrong, and naphthalamides based on ICT and EICPT features. Here is some short CV of Professor Okamoto because the time is very limited, so I only have his short CV. So Professor Okamoto from, as I said before, from Okayama University, Japan, from Department of Chemistry. His research areas are organic photochemistry, chemiluminescence, functional chemistry, lumination sensor, and synthesis of pi extended aromatic molecules and their evaluation as organic electronic materials, and also development of novel chemiluminescence materials. He have so many publications with 88 publication index by Scopus with Scopus X in 21. Professor Okamoto, are you already joining us?
Yes, thank you.
Okay. So because we only have limited time, here's your time for the presentation time. The time will be 20 to 30 minutes and then continue by discussion time about 5 to 10 minutes. So Professor Hideki Okamoto, screen and time are yours.
Okay,
Please.
now I'll share my slides.
Yes.
Can you see my slides?
Yes, I can see it clearly. Just put it on slideshow. Okay. Yeah, that should be good.
It's okay?
Yeah, it's good.
Okay, thank you very much, Anna, for kind introduction. And I'd like to thank all organizing committee members of this nice symposium to invite me and to give this opportunity. Today, I'd like to introduce our studies on fluorescence materials, and namely amino and amide substituted aromatic imide compounds based on ICT and ESIPT features. So let me start my introduction. This slide shows our project. We have mainly 3 projects currently. One is synthesis and application, transistor application of large aromatic molecules, namely the compounds having the zigzag benzene ring arrays. These compounds can be applied for the electronic materials such as organic field effect transistors. Second is photochemistry of cyclohexane compounds. We are interested in the photochemical dimerization of benzene cores in the cyclohexane compounds. Usually, benzenes never undergo photochemical dimerization, but in several special structures, we can observe the dimerization of benzene rings in such manner to produce octahedrons. And by introducing the fluorine atoms, we can modify the photochemical reaction modes. The third is about the fluorescence materials. We are synthesizing and evaluating the substituted aromatic imide compounds like this and like this. We try to manipulate fluorescence materials by using several mechanisms. So today I'd like to introduce this topic. So today I will present two topics, and one is fluorescence manipulation by ICT features. ICT means intramolecular charge transport by using the amino substituted aromatic imides. We can modify the fluorescence properties of these compounds through intramolecular charge transfer. The second is fluorescence properties of these compounds substituted phthalimides and naphtalimides. These compounds undergo ESIPT, that means excited state intramolecular proton transfer. So let me start with the first topic. So we are using the phthalimides cores, and generally non-substituted phthalimides very weakly even non-fluorescent material. This is because based on the electronic features of these compounds, the HOMO locates on the carbonyl moieties. That means the HOMO is non-bonding electrons of the carbonyl oxygen. In contrast, LUMO is pi star orbital of the phthalimide core. So by promoting the electron to the HOMO to LUMO, the excited states have n pi star electronic characters. In contrast, by introducing the amino group into the phthalimide core, the HOMO is the pi orbitals, including the amino group, and LUMO is pi star orbitals. So by introducing the amino functionality, the excited state electronic character is changed to intramolecular charge transfer from amino part to imide groups. So upon photoexcitation, such compounds, the electronic dipole moments markedly change between the ground state to the unexcited states. So due to the big difference between the electronic dipole moments, we can modify the fluorescence properties of ICT fluorophores by external stimuli such as solvent effects and external stimuli. So the fluorescence manipulation mechanism for the ICT fluorophore is summarized in this scheme. So first, ground state compounds absorbs the light energy to produce excited states. The excited states molecule solvated in a manner the same as the ground state. Then these compounds stabilized within the excited states electronic structure, including different solvation mode. And these compounds then fluoresce to produce fluorescence. So if we can modify the extent of stabilization with the solvent effects, we can modify the fluorescence color intensity and so on. So actually, we use the when we observe the fluorescence color of these compounds, we can actually see the fluorescence color change of these compounds with naked eyes. So this video shows the change of fluorescence color by addition of different solvents. So when we add ethanol to the solution on this one, we can actually see the fluorescence color change. So by using ICT molecules, we can probe the solvent effects and environmental situations. So conventionally, such compounds is constructed with the donor and acceptor type aromatic molecules. So these compounds are typical ICT fluorophores, and the 1,8 amino substituted 1,8 naphthalides is one of the most investigated fluorophores, and 2,3 naphthalides also solvents to responding to fluorescence materials. Interestingly, the compounds related to the this fluorophores, this compound shows the potential anti-cancer activity. So various materials can be have been synthesized and evaluated for the anti-cancer activities. So also, such solvents responding fluorophores can be used in monitoring the biomolecules interactions. So these oligopeptide, including the solvent depending fluorophores, have been used for the such purposes. So we are investigating donor acceptor type naphthalides from the viewpoint of fundamental photophysical properties. So we are interested in the substituents position of 2,3 naphthalides and 1,8 naphthalides. So we have prepared several possible isomers difference in the substituted position of the amino groups. So we systematically investigate these compounds to respond to the solvent effects. So this figure slide shows the fluorescence spectra of these three molecules. So one amino substituted compounds shows only moderate fluorescence-dependent solvent-dependent fluorescence properties. So from the hexane to ethanol, so this compound shows some slight rate shift of fluorescence. In contrast, this amino, 5 amino compounds shows a marked solvent-dependent fluorescence shift from hexane to 423 nanometer to in methanol 589 nanometers. So these compounds shows the marked fluorescence-dependent fluorescence color change from blue to red. The 6 amino compound shows the also shows the solvent-dependent shift of fluorescence color. So we can change the fluorescence color by external stimuli such as solvent effects. Also, we found that solvents amino substitution position is important to control the solvent dependence. for these compounds. So this picture shows the actual fluorescence color of these compounds as shown from the fluorescence spectra. This one amino compounds does not respond to solvents, and this compound change colors from red in methanol to green in acetonitrile. So we can modify the fluorescence color by changing the solvents effect and the substituent positions. And this is the fluorescence spectra for the 1,8 naphthalamides. So this compound does not respond to fluorescent solvent effects. This shows wide fluorescence shift, and this compound shows an intermediate fluorescence shift depending on the solvents. So these solvent effects can be explained by the Lippert-Matara analysis. So this equation is called as Lippert-Matara equation. So this equation shows the wave number difference between the absorption and the fluorescence correlated with dipole moment change between the excited state and ground state. So by plotting the wave number shift, and this delta means polarity function of the solvents. So this plot shows the difference between the dipole moments between the ground and the excited states. So these three amino compounds shows most steeper lines. So these compounds is most largest shows the largest dipole moment change between the ground state and excited states. And these four amino compounds shows significant solvent dependence, but this plot is almost flat. This may be explained by the efficient conjugation from the amino group to carbonyl compounds, both in excited and ground state. So both the ground state and excited state may be both polar character. So the polar character of these compounds can be explained by the molecular orbitals, and these compounds shows the HOMO and LUMO were conjugated from the amino group to the carbonyl parts. So both the ground state and the excited states both polar character. And this slide shows a brief summary of this amino substitute imides. So by using these compounds, we can modify the fluorescence features, namely rainbow colors observed from this compound and this compound. So second topic is fluorescence manipulation by ESIPT features. And ESIPT concept is shown here. This is a typical excited state intramolecular proton plasma compounds. From the ground state, the OH compounds is transferred onto the neighboring amino group nitrogen to form the tautomer form. So this compound shows the fluorescence emission from this tautomer form. Because the fluorescence absorbing, light absorbing form and the fluorescence form is totally different in the structure. So this compound shows the various interesting features. So large stock shift means difference in the absorption and fluorescence wave number shift, and such proton transfer usually water fast process, and so the proton transfer is involved. So this process is sensitive to hydrogen bonding, and so on, so on, and so on, so on. So, so generally, in the ESIPT processes, and most compounds have the OH functionality as proton donors. And NH proton is also used for the ESIPT to construct the fluorescence compounds. So first NH type fluorescence compound is recognized in this compound. So the NH protons can be transferred onto the carbonic atoms, oxygen atoms like this, and the tautomar form gives the fluorescence. So by comparing the OH and NH type ESIPT molecules, on nitrogen atoms, we can introduce additional substituents. We can modify the fluorescent character by change substituent on the nitrogen atoms. These are such examples. They can effectively modify the ESIPT fluorescence characters by the substituent on the nitrogen atoms. So we have investigated the ESIPT properties of these compounds, and this compound shows the ESIPT fluorescence to give the orange colors, and the protonation of this proton, NH proton, shows the green colors, and the addition of lithium ion produce the blue colors. So with the simple, these simple molecules can be produce various fluorescence colors by external stimuli. So recently, Professor Ando extended this concept to show the various color of fluorescence from this compound. So we produce to synthesize the phthalimide and naphthalimide having amide functionality here and here, and compare these substituent effect on the ESIPT properties. So these four compounds just different amide functionality here. This sulfone amide shows the red color and green color fluorescence, yellow color fluorescence through the ESIPT process. And this acetamide shows only normal form, no ESIPT fluorescence. And this compound shows the dual fluorescence here and here by normal form and ESIPT form. So we can manipulate the fluorescence colors by just changing a small part of here to manipulate the fluorescence color. This one is red, yellow, and this is blue and yellow. So, so I should skip this theoretical analysis, and let me show the fluorescence in the properties in the solid state. And these four compounds shows the fluorescence even in the solid state So these compounds is colorless in the under visible light, but under UV radiation, these compounds show the red, green, blue, and yellow colors. So we can clearly see the fluorescence color change in the solid state by just changing the small part of amide functionalities. And next one slide shows the fluorescence features of naphthalamides. So naphthalamides also having different amide group here shows the fluorescence as shown here. And these two compounds shows the blue to violet fluorescence as shown in the picture. No tautomar formation was observed through the ESIPT process. And in contrast, in the case of methane amides, we observe the normal fluorescence and ESIPT fluorescence and to produce the white luminescence from one molecule. So again, we can modify the fluorescence features, just changing the small part of these amide moieties. So in this case, these compounds did not show the ESIPT fluorescence, so the proton transfer process is energetically upfield and unfavorable. In contrast, the sulfonamide here shows the dual fluorescence from normal form and the tautomar form. So in this case, the proton transfer process is almost energetically even. So the both fluorescence from NH type and OH type structures can be observed. So so we investigated the deprotonation effects of amide proton here. So these compounds shows the fluorescence change, color change by extraction of the proton to produce green colors, and next calcium ion produce the further fluorescence color change to produce the blue fluorescence. So this compound can be used as calcium ion sensor. So this slide shows the summary of the second topics. We can manipulate fluorescent properties of this phthalimide and naphthalimide by just changing the small structure of the amide group. So let me thank the, my colleagues and students to support our studies, and Tatsuki, Aoi Tatsuki will present the hard work in the these student sessions. So now we are investigating the new fluorescence materials like this. So some days we present details of such studies. Okay, this picture shows my current research group. And I'd like to thank you for kind attention. And thank you. Terima kasih.
Thank you. Thank you very much for Professor Hideki Okamoto for the fascinating talk. I think you have shown us the fascinating research with amazing fluorescent colors from your compounds. So now we are moving on the discussion session. So we already have one question from Ibu Maria Ulfa, Siti Maria Ulfa. So she asked about what is the specific character of the compound having photoluminescence properties? And second question, can we predict what color shown after irradiation?
Yes, thank you very much for your question. So it's a very important point. The first question, so we can predict the electronic character by theoretical calculations. In this, in our case, the introduction of amino functionality will change the excited state electronic character from the n-pi star to intramolecular charge transfer ones. So in this case, the electron donating character of the substituent is important to produce efficient fluorescence and modify its fluorescence color and intensity based on the external stimuli. For second questions, so we have many information from the literature. So first, we can investigate literature to predict the fluorescence color, and also a simple theoretical calculations is useful to predict the fluorescence transition energies. Thank you.
Okay, thank you. Do you mind taking other questions? We still have 2 more questions for you. From Sania, she's a master student and she's also our MC this morning. She asked about, does stock shift has specific influence on the fluorescence characteristics? And then does larger stock shift give any influence to the fluorescence lifetime?
I'm sorry, internet condition is not so good, so can you repeat?
Yeah, the question actually also written in the chat room. If you can check the chat, if
Chat room.
Yes, from Sania about stock shift. So she asked about, does stock shift has specific influence on the fluorescence characteristic?
For which compounds?
I think for the compound, if the stock shift give some influence to the characteristic of the fluorescence color, maybe.
Maybe this one?
Stock shift. Hey, Sania.
This one?
Sania, if you hear, you can ask by yourself, maybe. So make it clear, your questions.
What I meant is, does a larger stock shift give any influence to the fluorescence lifetime? Because if stock shift influence the color of the fluorescence, does stock shift give any kind of influence to other kind of characteristic to the fluorescence other than the color? If that makes sense. Thank you very much.
Okay. So, for example, we can modify the fluorescence by external stimuli. So in this case, the solvent effects change the fluorescence colors. So these compounds can be used for the microenvironment of solvents to probe. So we can know the situation of the microenvironment of the solvents and where the fluorescence compounds exist. Okay, so in this case, we can find in this case, we can find either the ion for the external stimuli, then we can know the prove the lithium ion by using these compounds. So in this case, the protonation and deprotonation is also detected by the fluorescence colors and so on. So we can to design the fluorescence molecules for detecting the specific external stimuli. So by designing the appropriate fluorescence structure, so we can to construct suitable fluorescence probe for the purpose. Okay, so maybe I did not catch the point, so maybe we can discuss later. Thank you.
Thank you. Thank you. But because of time limitation, we only can take only one very last question. This question from Bapak Yuniar Ponjo. He's our head department of chemistry. So he asks about, will the position of amino NH2 in ortho, meta, or para in the ring give significant influence on the fluorescence ability of the compound?
Yes.
The position of amino, yes.
Yes, position of amino group is very important. So I'm just explain it briefly. So these compounds, amino group here. So the HOMO and LUMO is almost the same distribution on the entire fluorophore cores. So these compounds shows little intermolecular charge transfer nature. In this case, the HOMO distribute mainly the amino group here, but there is no electron distribution here, and mainly distributed and imide parts. So if electron promoted HOMO to LUMO, excited states will have the electron transfer feature from the amino part to imide parts. So this resulting in the part of electron is moved from amino part to imide part. So the excited state is more polarized than the ground state. So that is called charge transfer, intramolecular charge transfer character. So this characteristic excited states has larger electronic dipole moments than ground state. So such electronic character will respond more sensitively to external environment by solvent effects. Okay, thank you.
Okay. Thank you very much for Professor Hideki Okamoto. Because of time limitation, we now need to move on our next speaker. Thank you very much once again for your great presentation. Please give a round of applause for Professor Hideki Okamoto. Okay.
Yes,
Okay, now, thank you. Okay, now we move on our second keynote speaker. We will have Professor Sakurai, Professor Hidehiro Sakurai from Department of Chemical Science and Engineering School of Engineering Science, Osaka University, Japan. Before Professor Sakurai start his presentation, I will show you his short CV. It's very short CV here that I have. So Professor Sakurai from Engineering Science, School of Engineering Science, Osaka University, Japan. And the research areas of Professor Sakurai are nanotechnology and materials, functional solid-state chemistry, synthetic organic chemistry, bioorganic chemistry, life sciences, and structural and physical organic chemistry. He has so many publications with 186 publications in Scopus Index and also with Scopus X Index 36. The presentation title for this morning is Recent Progress in Sumanen Chemistry. Professor Sakurai,
Okay.
are you here
So
joining us?
So
Yep.
can I share now?
Yes, please.
Okay. Did you approve the sharing?
Yes, for the
Okay.
yes, and you are our co-host too, so you can share the screen.
It's rejected now.
You should do that. You should be able to do
so
it.
sharing is rejected now. So
maybe you can try it again.
Okay. Try again.
Please, yes.
It doesn't work.
Oh,
it seems like there is two accounts for Professor Sakurai.
Okay. Try
Maybe the other one.
To account. It's only one account.
Okay. So somewhat the sharing is rejected. So I try to. Okay, I try again.
Okay. Sorry, take your time.
Oh no,
No, not
always
working.
always rejected. So the access can okay, just okay, security and privacy.
Maybe Bu Siti Mariam can help for sharing the PowerPoint. Maybe.
I don't have the PowerPoint from Professor Sakurai.
Yes, we can help. Yes, we can help sharing your presentation if you like. Maybe you can send us the PDF file for your presentation, and then.
Okay, just a moment. So the why the sharing is rejected. Why the something happens about the security.
Maybe your laptop, the security. Sometimes if we share screen, we need to type in our password in our own laptop.
Anyway, so I try to find out the solution.
Okay.
Anyway. It looks okay, but somewhat always rejected. So oh my God! So it's quite strange. So even the desktop cannot be shared. So it is a very first experience for me. Sometimes it happens in case of the sharing the slides itself, but this time, so I couldn't share even the Sorry, I need to close the session first, right? Then I will enter again. Is it okay?
Yes.
Or can you change the speaker or something?
Are you okay if we skip the next speaker and then we go back to your session? Is that all right? Oh, I think he's on.
He already left.
Yes, okay. Maybe while we waiting for Professor Sakurai, maybe we can move on to the next speaker. If that's okay with Ibu Maria Ulfa? Or
But Professor Nishizawa haven't joined yet.
Okay, okay. So
oh
now
yeah.
I come back. I
He's
come
joining,
back
okay.
and try to share. Okay, I try to share the. Oh, still not okay.
We are happy to help you share screen from our committee member, so we can share your presentation.
Okay, so okay, I'm sorry. So I prepared my. Okay, I prepared my file as a keynote, so that I now try to convert to the PowerPoint. Can you wait a little bit?
Yeah, sure.
It should be very heavy, so that. Oh, sorry, it's too heavy, so that it's maybe how to solve the problem. Okay.
Yeah, I think in this case, maybe we can move on to the next speaker, and then
Sorry for that. So that I try to find out the solution.
We are sorry too. We apologize for this inconvenience, and then maybe you can send your PDF file using Google
now
Drive.
I try to reduce the size of my PowerPoint file, so that sorry for that.
Okay. For the next speaker, before we coming back to Professor Sakurai, we will have Professor Mikio Nishizawa from Rutsumekan University.
Okay, hello everybody. So I'm
good morning, Prof.
Suddenly change the speaker.
Are you okay?
Sometimes it may happen. So I will share my slides.
Yeah, try
just
it
a moment.
See if it works.
I think it will work.
Okay,
can you see?
It's working. Yes, it's working. Yeah, I can see it
Okay,
clearly.
so from the first slide, I'll explain my topics. So thank you for the introduction. And today I'm talking about approaches to investigate pharmacological effects of crude drugs used in Japanese Kampo medicine. And it is some collaboration with the people in Brawijaya University. So today I'll talk about 3 points. At first, I'm introduced about this study, and second, one example about the rhizome of Conidium officinale. It is done by Febi from University of Brawijaya. And second one is as an example about beta melon fruit. It is administered to diabetic model mice. It was done by Dinier from Brawijaya University. And I'll briefly explain about this study at first. So, you know very well about several drugs, very popular drugs, such like chloroquine or aspirin or paclitaxel or ivermectin. These drugs comes from natural sources, such like a medicinal plant or bacteria. For example, chloroquine comes from the bark of quina. So we know very well about quinine. It is alkaloid of the natural product. And similarly, the aspirin, it is an acetylsalicylic acid, comes from the bark of white willow, Salix alba. At first, it was developed as salicylic acid, but it has very strong side effect, adverse effect on our stomachs. And then the stomach ulcer will occur by salicylic acid, but it was modified by salicylation. Similarly, the paclitaxel is anti-cancer drugs, and the recent one is ivermectin for filariasis and onchocerciasis. It comes from bacteria. So these drugs comes from natural plants and bacteria. So it is a good source for study. So you can imagine these drugs. You can figure out the drugs from plants or foods. So in this case, chemical purity as x-axis and pharmacological potency by y-axis, we can know the plants or foods has low chemical purity and also very low pharmacological potency. But if you see low molecular weight drugs such like aspirin has a very high purity and high potency. But our drugs, like campo drugs or crude drugs located here, so less purity, less potency, and functional foods located here between plants or foods and crude drugs. So the jamu, it is very famous one in Indonesia. So jamu includes several herbal drugs. So it contains like a plant or foods, in some cases crude drugs. It has variety of plants which has chemical purity and chemical potency. So our aim is to clarify crude drugs, or jamu is also included, such like a crude drugs to investigate. So our target is like this, such like roots or radix, or such kind of flowers or fruits. So it is included as campo drugs, or sometimes called campo medicine, traditional Japanese drugs. And nowadays, many Japanese medical doctors, including me, can prescribe campo drugs, and most medical doctors prescribe for every day. So our formulas, including this campo drug, is 148. It is defined by Japanese pharmacopoeia for its quality and the recipe. So in our study, we will do like this. So Urfa-san has already done, and Dinya-san, Febi-san already done this kind of things. So it is leaves, in this case leaves, and extract with methanol, and then evaporate the methanol and obtain methanol extract. In some cases, we use hot water extraction, but it is less efficient. So we prefer methanol extraction. And our strategy to obtain chemical drugs is like this. So from this kind of medicinal plants or functional food to obtain extract, and biological assay or pharmacological assays are done, such like a nitric oxide assay in hepatocyte, in some cases macrophages, and purify by several methods, chromatography and so on, and obtain pure chemical compounds. And then we will do NMR or rotation or several things to obtain chemical structure. In this case, we use mass spectrometry also. I'll explain later. And then these kind of compounds are obtained, then we can do use as a development of new drugs. So it is a slowly from the medicinal plant to obtain this kind of compound. So typically we use crude fractionation using ethyl acetate and N-butanol. And then we can partition successively by ethyl acetate and then N-butanol, unless it's water-soluble fraction. So usually ethyl acetate soluble fraction is called as fraction A because acetate. So fraction A, it includes phthalate or terpenoid and oil, flavonoid, and so on. So it is most potent or much more efficient to give high pharmacological activity. Today's example is phthalate as thank you, and terpenoid is a bitter melon fruit. And we can also obtain this fraction B and C. So why, why B, it comes from butanol. So A and B and then C, that's simple. And fraction B has amphipathic compounds such as glycosides, saponins, and tannins, and alkaloids. This works as prodrugs. It is metabolized by microflora, I mean the intestinal bacteria, and absorbed in the intestine and transferred to the liver. And water-soluble fraction C, it contains sugars or peptides. This portion is like a black box. It is very difficult to investigate. But now the Saki Shirako, assistant professor of at my laboratory, we are doing this analysis. So introduction is like this, and then I'd explain one example about anti-inflammatory effects of the rhizome of Conidium officinale. Maybe Conidium officinale is not common for you, but it is very common in Asia, especially East Asia, such like flowers. And this is a rhizome, not a rocks. It is a rhizome. And the Latin name is Conidium officinale. And we use this rhizome for the assay. Sorry. Okay, so this white flowers. And this medicinal plant, Conidium officinale, has been used for a long time. In Japanese name, it calls senkyu. And in several Kampo formulas, senkyu is included. For example, there is 3 examples. Jumi hydroctol to treat eczema and urticaria. And next one is to treat rhinitis. So anti-inflammation. But the third one is very good for women to treat menstrual disturbances and some other disorders for women. So it is very good medicine, Kampo medicine for women, and also has an anti-inflammatory activity. So we check this anti-inflammatory effects, anti-inflammatory activity for this study. So the main constituents reported are phthalate, such as these things, phthalate. So we focused on this phthalate and to investigate its anti-inflammatory activities. So Feby has done like this. So nearly 1 kilogram of rhizomal Conidium officinale is extracted and obtained methanol extract and fractionated into 3 crude fractions. And ethyl acetate soluble fraction called fraction A, she obtained and purified 4 phthalate, this butyrylphthalate, quinidilide, sanchinolide A, and neoquinidilide. It is a very complex way, so I omit the procedures, but she purified and determined its chemical structure by NMR. So this is a pharmacological assay using primary cultured rat hepatocyte. This hepatocyte comes from wether rat liver. And this liver was perfused with collagenases. And collagenase digests extra material matrix, such as collagen. And then the cells will be dispersed and we obtain primary cultured rat hepatocyte like this. And we add pro-inflammatory cytokine, interleukin-1 beta. Interleukin-1 beta causes inflammation in hepatocyte and gives high rates of nitric oxide production. So if we see the nitric oxide levels in the medium, we can know the levels of inflammation. And in reverse, so if we add fraction or constituent in the medium together with IL-1 beta, the IL-1 beta induced nitric oxide production is suppressed, okay? So it is very simple way to assay the inflammatory levels. So we prefer this method also all the time. It is very simple one, and even undergraduate students can do it. And very precisely it can be done. So we use this nitric oxide production system. And also medium, we can measure LDH activity, lactose dehydrogenase activity. LDH is located in the cell. So if the cells are injured, then LDH will be released from the cells to the medium. So if we measure LDH activity, then we can know cytotoxicity of each fraction or constituent. So we only measure production levels and when LDH activity is not observed. So no cytotoxicity is observed, we measure production. It is a principle. So it is an example, fraction A and fraction B and fraction C. This black bar shows IL-1 beta induced production of NO in the hepatocyte. In this case, it is very high. And then fraction A is added at this concentration. Then the IL-1 beta NO level becomes lower. So it is suppressed. Similarly in B, but C did not affect it. So if we know the Western blot analysis, NOS protein is like this. So IL-1 beta gives a high INOS protein expression, but it is reduced. In B, also reduced. C does not affect, did not affect. So it is very simple way. So then it is a little bit sophisticated way to check this phthalate. So Feby obtained 4 phthalate and the linguistilide. It is very common, not only Senku, but also other herbal plants. So in this case, we bought this linguistilide. Feby did not purify, but she purified these 4. And then if the range is approximately set, then we can measure the level of this compound, each compound in the fraction A. So we can measure this like this. So in this case, compound 2 is this peak, and then the level is checked, then fraction compound 2 gives this peak, and this one 3s butyl phthalate is this peak. Similarly, we can obtain, and sanquinolide A, it is 4, peak 4. It is a most abundant. So similar way, sanquinolide A gives a good suppression, and inosprotein expression is inhibited by sanquinolide A. So it is very simple way. If we obtain the cells of the primary cultured hepatocyte, we can see the suppression of inos messenger RNA and also tumor necrosis factor alpha, TNF alpha messenger RNA, and also IL-6, CCL20, CCL2, these chemokines, and also lipocalin 2 messenger RNAs. So we can know anti-inflammatory effects are seen by this by RT-PCR, quantitative RT-PCR using primary culture rat hepatocyte. It is a summary, just this Conidium officinalis sanquirhizome gives this constituent, and this constituent blocks the IL-1 beta induced inflammation. So it is one example. Then let's go to the next example. It is a beta melon fruit in diabetic model of mice. So maybe many people know this beta melon. It was taken, this photo is taken in Malang or around Malang, not in Japan. In Japan, very similar beta melon is obtained in Okinawa area in the south part of Japan. So beta melon fruit is very famous as pare or goya in Japan. And this beta melon fruit has been used to treat microbial infection and also to treat diabetes mellitus. So we try to find these activities, anti-inflammation and also anti-diabetic activities. So it is our aim for this study. So it is a very similar way. So beta melon fruit, but linear use 20 kilograms of beta melon, this one, 20 kilograms. So it is very large amount, but should be freeze dried. Otherwise, water is too much. So she fractionated into fraction A to C. The most active fraction is fraction A. So ethyl acetate soluble fraction. So this is an example of the HPLC profile of a subfraction, purified subfraction. You can see big peak. It is identified as cucurbitacin B. Its chemical structure is like this. It is some cucurbitan type terpenoid, one terpenoid. In this case, 60% purity cucurbitacin B is obtained, but this purification is very difficult. So to remove chlorophyll and then purified. But fortunately, we can obtain the cucurbitacin B commercially. So we use as a standard, and we identified and we use pharmacological assay to measure NO production in hepatocyte. So you can see here, so beta melon fruit fraction A gives such kind of suppression. But cucurbitacin B gives similar way. But please note this unit is nanomolar level. Usually micromolar level of suppression is observed. So this cucurbitacin B gives them the most, I would say it is the most, the highest activity in the suppression of nitric oxide. It is almost similar to dexamethasone. Dexamethasone, it is one of the very famous steroid drug. It is similar. So, but the contents of cucurbitacin B is very low. So next question is this cucurbitacin B or cucurbitacin B containing bitter melon fruit fraction A will give anti-diabetic effect or not. So we use this mice. So left one, it is a wild type mice, very small. Someone says it is cute. It is very difficult to say, but this one, right one is OB mice. It is a mutation. It has mutation in the leptin gene, and leptin gene is responsible for satiety. So this OB mouse will eat excessively, very large amount of diet. So we use as OB mouse as diabetic model mice. So linear fed a diet including 1% bitter melon fruit fraction A or a diet alone for 7 days, and check body weight and blood glucose level. And after euthanization, we analyze gene expression in the liver and immunohistochemistry. We use 4 groups. So wild type bitter melon fruit fraction A minus or plus, and obese mouse minus and plus. So 4 groups, okay? So it is left side is a body weight. So you can see here, wild type is lower body weight, and OB mouse has a higher, of course. And you can see the asterisks. It is a statistically significant, it means. And OB minus BMFA, so diet alone gives a higher, but if OB mouse were fed by BMFA, bitter melon fruit fraction A, then it gives a lower body weight. And interestingly, the blood glucose level becomes lower in the mouse, in the OB mouse fed BMFA. So bitter melon fruit fraction A works to reduce blood glucose like this. So every day she cut small incision on the tail and take a small aliquot of blood and check blood glucose. So it is significant differences at the day 7. And also you can see here the ELISA data about serum insulin. So it is left side is wild type, right side is OB mice, diabetic model mice. So if we administer bitter melon fruit, then the serum insulin level becomes higher, significantly higher. And also we checked insulin receptor in the liver. So we take liver specimens by each mouse. So 4 mice for OB mice per group. And then, so you can see the band of insulin receptor alpha, the wild type, it has higher, and OB mouse, but without diet alone. So diabetic mouse gives a very faint one, but it becomes, the intensity becomes higher here when bitter melon fruit was administered. So it is a clear differences. And then it is a histochemistry of bitter melon fruit administered mice. So wild type is this line, and OB mice this line. So left side is HE stain. So you can see white big droplet. It is a lipid. And these lipids are stained by all red or stain by other staining method. So white type, there is not so much differences, but please see the left lower right side. So this one is orange portion is oil stained lipid, but it becomes smaller. So it is a clear differences. And to confirm this, we measured triglyceride and cholesterol in the liver. So it clearly shows that OB mice gives a reduction in triglyceride. And also we confirmed after taking serum. So lipid in the serum lipid level and cholesterol level becomes lower. So all the data confirms that the anti-hyperglycemic, anti-hyper cholesterolemia or hyperlipidemia. So bitter melon fruit works very well to the OB mice. I did a summary. So cucurbitane type triterpenoid, maybe it is a principal constituent and has main pharmacological activity. It probably has a hypoglycemic effect, and also so the increased expression of insulin receptors. So and reduce insulin resistance. So this works as anti-diabetic effect. So it is just before the final. We are now, I'm a project leader about this project until March 2023, and we are doing some kind of anti-diabetic approaches using traditional campo drugs and also traditional drugs jamu. So maybe if we have interest, please collaborate and do such kind of anti-diabetic approaches using herbal drugs of foods. So this is my students. So here is Feby, and here is Dinia, bitter melon, and thank you, they did. And Widodo Sensei is here also. And now we have a very strong staff, Saki, Shirako, it is and also there are many students, very powerful students in my lab. So we thank all these students and people who collaborate with me. Thank you very much for your attention.
Thank you very much for Professor Mikio Nishizawa for your great talk. Now we move on to the discussion section. We already have so many questions for you, but because of the time limitation, I only choose 3 of them. Is that all right? Or maybe for the rest of the question, you can answer directly to the chat session. So here is the question for you. Maybe is it better if I show it in the screen so you can read the question? So this is 3 questions that I choose from the participants, from students. They are from Brawijaya University. First from Ferry, maybe she's also your student. He has question related to the NO assay. Is it possible that the compound decreases the NO production, but the level of inos remains stable or unchanged? Does a compound can inhibit inflammation by affecting enzymatic activity of inos? So even the expression of inos may unaltered, but the NO in the medium has decreased.
Thank you very much for the question. It is a very interesting question for us. And usually the inhibition or suppression of nitric oxide production is involved in the suppression of transcription of iNOS gene. So in that cases, the enzymatic activity of iNOS was not affected. In some cases, it may happen. So we can discriminate this enzymatic inhibition by some inhibitor to iNOS, but usually it is different. We can discriminate this one. So one example is ETAS. I wrote one paper about this kind of discrimination about enzymatic suppression and transcriptional suppression. Maybe I can later send this paper to you, or you can access this one. Thank you very much. And
sorry. Okay, so we move on to the next question.
One.
Yes, the second one from Jonathan. He's also a student in Brawijaya University. From what he knows, most of the bioactive compounds in herbal plants are unstable. How to ensure that we keep the maximum bioavailability of the plants in the extraction process for medicinal application?
Okay, this is also a very interesting question. Usually we apply 50° or 55° for the extraction of methanol. Many researchers ignore the degradation during this extraction. So usually it is protected by many compounds, similar compounds. Of course, some degradation may occur during extraction, but we ignore these points. So you can ignore it, I think.
So maybe we just use the low temperature for the extraction process. Okay, so for the last one from Andrian from Brawijaya University, he want to ask about the type of animal model that should be used for diabetes mellitus type 2 experiment. Is it better or using Wistar rat or Babsi mice?
Usually we use OB mouse. It is very expensive, but we use this one. And other models are streptozotocin administered rat or mice. It is also possible, but it takes some time. So 1 month or less than 2 months. So it is also possible. But of course, doses should be adjusted to obtain type 2 analysis, type 2 diabetes. Yeah, it is possible.
Yes, and also based on our budget, maybe in Indonesia we use Wistar or Babsi because they are accessible and easy to obtain. Not OB is not really easy to obtain here.
Yeah, so maybe streptozotocin is the best way to use.
Yeah, I use streptozotocin to induce diabetes to my Wistar rats. Okay, thank you very much for all your answers. Now we move on for Professor Sakurai.
Okay, very sorry about the trouble, and Nishida Sensei, very sorry for the such kind of trouble, and thank you so much about
no problem. Sometimes happens.
Yes, yeah, your handling is very helpful to me. Okay, so I now try to share.
Okay,
it works.
It works.
Okay.
So what happened before?
Actually, because my system was set up as a very highest secured system. So that now I unlock the firewall. So now it works, I guess, right?
Yeah.
So can I start my presentation?
Yeah, sure. Yeah.
So for 25 to 30 minutes, right? Okay. Yep. Okay, first of all, so I'm Sakurai Hidehiro, and from the Osaka University, and I'd like to thank all of the organizing committee of this symposium and to invite me and also my student, Pete. Maybe she will give a talk later about to participate to such kind of a wonderful online symposium. But I'm very sorry to make you have so many trouble. And okay. Anyway, so I initially planned to show some movie about our chemistry department, but I skipped that. Anyway, so I only show can you see that the cursor the pointers now? It works? Okay.
Yeah.
It doesn't?
The movie? Where's
Pointer. Did you see the pointer?
No.
Okay. How to? Okay. So Anyway, so this is my group members, and okay. So now the 40% of the approximately 40% of the students are coming from abroad in my group, and now the two Indonesian student is working with us, and Wilda, so she's coming from your university. And also the Isan is one undergraduate student from the Indonesia is now joining us. So we have 11 different languages homepages. So that we also provide the Indonesian version. So that if some of you are very interested in joining us in the future, so that please screenshot of this the QR code and access to the Indonesian version of our homepage, if you are interested. And our group is now mainly dealing with the four different fields, not only including the organic chemistry, but also the inorganic and the physical chemistry. So the one is the buckyball chemistry. This is curved conjugated material systems, and another is a metal nanoparticle catalyst, and the third one is the porous and dynamic, so mobile molecular crystal system, and the fourth one is the solution state laser ablation system that we want to apply the laser system into the synthetic chemistry. But anyway, so mainly today, so that we focus on the two major topics. The one is the buckyballs I'd like to talk from now. And the second topic is the metal nanoparticles catalyst should be given the presentation by our student Pete in the later. So that I won't only focus on the buckyball chemistry. So that you may know that the carbon allotopes the chemistry is quite now widely expanded. So since the discovery of the C60 and the carbon nanotubes, so that now we are and also the graphene, the rediscovery. So such kind of pi conjugate is the systems is quite interesting for the development of the material sciences. So, but we are coming from the organic chemistry, so that we are much more interested in the partial structures of the C60 or cap structures of the carbon nanotubes. That is a ball-shaped molecule. So that is we call the buckyballs. So this is the kind of the fragmental structures of the C60 or the carbon nanotubes. So the starting point of the buckyball is of course definitely the buckyball is a fragmental structure of the furan or the carbon nanotubes. So that can be prepared through the top-down approach or the bottom-up approach by the synthetic chemistry. And that can be a very good motif for the further construction of the three-dimensionally aligned complex system of the carbon frameworks. And also thanks to the very unique structures of the ball shape, so that we can enjoy so many things by using these pristine structures. So, but we can consider about the two pristine structure of the buckyballs, because the buckyballs only consist of the combination of the hexagon and the pentagon. Then we can consider as a pentagon on the center, in the center of the molecule, that is a C5 symmetric. This is called coranulin. This is already synthesized in older than the discovery of the C60 itself. So the coranulin was the first synthesized in the 1966. But in contrast, that the sumanin is this is in another pristine structure is the hexagon in the center of the molecule, that called sumanin. So that was also the very important and interesting molecules, and having the three pentagon on the periphery. So that is also one of the very important compounds. But because that the pentagon can shrink the structures, so therefore that the coranulin's ball depth is expected as a 0.89 angstrom, but the sumanin is expected as a 1.1 angstrom. So that should be much more deeper. So therefore, that the spanning can should be the very much more strained and unstable molecules. Therefore, the no successful route for the synthesis of the spanning was discovered before. So such kind of ball-shaped molecules construction was the highly improved in 1990s since the discovery of the pyrolytic method, flash vacuum pyrolysis. That is a kind of the gas chromatography reactions. So the Larry Scott and the J. Siegel in 1992 developed a very straightforward method for the construction of the crinoline by the flash vacuum pyrolysis. So since the discovery of this process, so the crinoline its chemistry is highly improved, and now the crinoline was commercially available. So therefore, that there's so many papers appears by using the crinoline. But very fortunately, unfortunately, by using the similar approaches, the Professor Mehta in India tried to synthesize the summanin through the flash vacuum pyrolysis method by starting from the triphenylene unique moiety. But monocyclization and the dicyclization happens. But even that, the summanin could not be synthesized by using the flash vacuum pyrolysis. So that means that so many organic synthetic chemists tried to synthesize the summanin, but always failed. So therefore, the summanin chemistry was totally delayed, almost 10 years back from the crinoline chemistry. So, but very fortunately, in 2003, the Taro Daikoku is my student, succeeded in the synthesis of the summanin by only the 3 to 4 steps from the commercially available norbornadiene by using the simple flask level reactions. So that involving that cyclotrimerization of the norbornadiene and tandem olefin metathesis to convert to the hexahydrosummanin, then finally the DDQ oxidation to form the summanin. So that does not include any specific or the very special reaction conditions. We can manage all the reaction under the usual flask level reaction. And then, so that we can now synthesize the summanin in the 100 milligrams on the gram scale per week, and very constantly. So now we can get the summanin enhanced very, very easily. So that I'd like to summarize that the property of the summanin. Summanin is a kind of the 1/3 structure of the furans, let's see, C21. And in the solution state, it can flip. So the ball shape is interconvertible. And in the solid state, thanks to the ball structures that can stack very easily, very beautifully perpendicularly, that can induce the electron conductivity or other physical properties. So that just let me show that typical the properties of the solid state of the summanin. So that I already showed you that summanin should possess the unidirectional columnar packing in the crystalline state. So that induced that the anisotropic electron mobility in the perpendicular direction, and also the very large Zwick coefficient. That is thermal electricity, and also the summanin possesses a very nice liquid crystalline mesoderm. So that is induced by the thanks to the very unique perpendicular packing structures. And so that I just this is an example of the electron conductivity. And on the other hand, the crinoline C5 symmetric another pristine structure of the crinoline. You can see that the crinoline packing structure is not like columnar structures. So therefore, the pristine crinolines electron mobility is quite low. But once we just tune the substituent and the symmetry of the crinoline to the C2 symmetry, so that we can also align the crinoline crystal structure into the very beautiful perpendicular columnar structures. Then we can that compound that crystal shows the very high electromobility, much more larger than the pristine sumanin. So that means that packing control of the packing structure. That means the crystal engineering directly related to the physical properties. So that means the synthetic chemistry is very easy to contribute to develop the material science in this field. And also another important behavior of the buckyball is the ball-to-ball inversion. So that I already showed you that in the video. So the ball shape is interconvertible through the flat structures. So that is very easily observed in the solution state, so that we can change the concave phase and the convex phase by using these kind of the inversion processes. So recently we also found that such kind of the ball inversion process even occurs on the solid surface, so that we can very beautifully align that the sumanin onto the gold 111 phase. Then we can observe that the ball up sumanin and the ball down sumanin by the STM measurement. But very interestingly, that this STM tipping can induce the ball up and the ball down, the changing. So that means that this sumanin works as a kind of the on and off signals. 0-1 signal can be detectable by the change of the ball inversion process. So what it means is that such kind of a very simple ball structure it's possible to develop the molecular level memory system, because this is a 1-0-1 signal can be detected. So that means the molecular structure is quite small. Therefore, we have a lot of chance to develop the very highly condensed memory systems. So I'm sorry to show that this is a very old data of the development of the areal density of the memories in up to the 2010. So we reported that this system in the 2016. Then theoretically, the sumanin system can reach to the very condensed memory having the 600 terabyte per square inch meter. So that means a far systems can make the very, very highly condensed memory system, because that this is a very simple small molecule is a one unit of the memory. So, but of course, in reality, it's quite difficult to develop such kind of molecular level of the memory system. So we need to develop a lot of things for like a much more technological problems. But anyway, theoretically, we can reach to the very high condensed memory system by using very simple molecules. Then, in the carbon chemistry, so the doping with the other atoms, like a nitrogen or boron, is quite important to tune the properties of the carbon systems. So typically, the nitrogen-doped carbon materials are quite well developed and for the investigated for so many applications. So in the case of the buckyball chemistry, we can also consider the nitrogen doping systems, because just one or several carbons can be replaced by the nitrogen. But this is a kind of organic molecules, and so many drastic structure change will happen by the replacing from the carbon to nitrogen, such as a bond length is significantly shortened by the changing the carbon-carbon bond to the carbon-nitrogen bond. So that induced to shrink the structures, and the bond depth should be much more deepened. So shorter bond length induced a very deeper and a very strained bond structure. Therefore, from the viewpoint of the synthetic chemistry, it's very difficult to develop the nitrogen-doped systems. So that nobody succeeded in developing the nitrogen-doped buckyball before. But we can do the very synthetic approaches, because this is a kind of a total synthesis. So since we are the synthetic chemists, so that we can develop the very rational synthetic route, very similar to the original Sumane synthesis, but route is much more complicated in reality. But finally, we can get that try other Sumane moieties through that stepwise synthesis. So now we can measure that. Okay, so we can measure that the structures. Then even such kind of very deeper ball, so that we can directly observe the ball inversion can happen even by using such kind of very deeper ball. And the ball inversion barrier is reached to the 42.2 kilocalorie per mole. So that means this is never flipped at the room temperature level. So the half-life of the ball's flipping is 57 billion years. So such kind of a very stable ball shape, but it can flip up to elevated temperature such as 488 Kelvin. So then, finally, my postdoc, Dr. Tan, can synthesize the pristine triazosumanin by the struggle. He struggled for optimizing this condition for more than 1 year, and finally he was able to make a pristine triazosumanin. And maybe we need to notice to you that this triazosumanin has intrinsic chirality thanks from that the positional nitrogen, position of the nitrogen. So therefore, that the erancho pure triazosumanin shows the very beautiful helical packing structures. This is quite different from the achiral, the sumanin structures. So the chirality can induce the helical packing structures that can be also applied to some nonlinear optics or other applications. Then, but we tried to submit this paper. So the reviewer always asked us that how about the racemate? Yeah. So in the case of the racemate, is it a mixture of such kind of helix or the other structures? Then another student, so Dr. Pachlin Kelmati, so from Thailand, and she also tried to get the racemate crystal structures. Then we found that the racemate shows a very beautifully perpendicular columnar structure, almost the same as the pristine sumanin itself. So that means that we can very precisely engineers that the crystal packing structures of such kind of ball-shaped molecules. That should be very interesting. Oh, sorry, that's back. Okay, so the rest of the times I'd like to show that some supramolecular chemistry by using the sumanin moiety. So by extending the peripheral aromatics position to the ester, that has a lot of trouble of the synthetic chemistry, actually. But Todakone, my previous student, finally developed the very nice esterification reactions. Then now we can make several types of the ester derivatives, the hexa ester derivatives of the sumanin. So that the sumanin shows the very unique liquid crystalline structure, assembly. So usually such kind of the liquid crystalline assembly requires so many carbon chain lengths, but we can only introduce that only 6 chain. That is good enough to show that the liquid crystalline phases. So this is also very unique for any other systems. So this is of course this is a hexagonal columnar liquid crystalline phases. So then you can see that the sumanin, the liquid crystalline, is quite soft compared with the other systems. So these are you can see that the very similar liquid crystalline of the triphenylene system. This triphenylene, the liquid crystalline, is usually very solid. it's like almost wax or something like this. So it's very solid. But the Sumanen structure, the liquid crystalline, is quite soft. So maybe why does such kind of the Sumanen liquid crystalline shows a very mobile and soft liquid crystalline state? That should be thanks to the like a kind of the bowl-shaped stacking shows the very flexible alignments, allows the flexible alignments. That is a very unique properties of the bowl-shaped assembly systems. Okay, so okay, maybe I can have still a couple minutes, so that maybe I will show the several slides about the Sumanen supramolecule systems. So by using the bowl shape, the motif as a unit of the supramolecules, we can also enjoy the several things. For example, that hexagonal hydrogen bonding networks always provides the very flat seed structures assemblies. So, but the Sumanen has a bowl shape. Therefore, that cannot form such kind of clear flat sheet structures. So how nature solves the such kind of the frustration by the bowl shape. So we can prepare several the corresponding the hexacarboxylic acid, and we can find that the two different crystals. So this polymorph was observed. And these two guys has shown the two different types of the seed structures. One is the really wavy seed structures. That is a kind of the easy to imagine that how to solve that the bowl problem. So this wavy sheet is also very unique, but very unexpectedly we can get the double layered structures as well. So that means two such kind of wavy structures is combined together and form the kind of the like dumbbell type layered structures. So this is a kind of the two types of the layer structures, and the most interesting form is the form 3, and because that I want to skip that because that this bowl shape seed can shrink by under the pressure. So that means the bowl, can be slided and shrink down to only the C axis direction. So that means that under the pressure, A direction and B direction doesn't change, but significantly C direction shrink down. And after releasing the pressure, that is slowly go back to the original form. So that means that this bowl-shaped network structures show the anisotropic response under the pressure. So this is a quite unique that non-flat sheet structures can be prepared by the hexagonal networking. And now I don't have enough time to show the details of the discrete pore systems. But anyway, so the discrete pore system is also quite important field in the supramolecular chemistry. And previously, such kind of the molecule is approaches through the bent ligand by using the bent ligand or the bent ligand with a large surface area. But these kind of the species can be directly prepared by using the curved pi ligand, right? By using the curved pi ligand, combination of the curved pi ligand, we can easily constitute or construct these kind of the spherically ordered discrete pore systems. So we can develop this ligand and apply to the supramolecular chemistry. And I don't want to show the details today, but by changing the metal source, we can develop the totally two different types of the supramolecular network system, having the spherical pore. By using the zinc, so the 3 Sumanen panels forms the one spherical pore. And in the case of the cadmium, so that we can develop the 4 Sumanen panel forms that very, very beautiful tetrahedral types of spherical network systems. So so now I don't have enough time to show the details, but anyway, so that you can enjoy that the structure or the aspect of these supramolecular networks. So then we can encapsulate the various guest molecule in the future, and this is a totally packed structures. For example, the aperture is only available in the 2.1 angstrom times the 2.1 angstrom. That means that even the helium cannot be passing through this pore. So that means that once the molecule is encapsulated in the network systems, so no molecule can go out. So that means that this is a very kind of the ideal the discrete pore the systems we can induce just by the method of the MOF chemistry. Okay, so I'd like to close that my presentation. So of course these kind of the chemistry should be contributed to the many the researchers, including our students and also the senior researchers. So I only show that the representative person of this contributor, the previously Professor Dr. Shuhei Higashbayashi, and currently Dr. Yumi Yakiyama and Dr. Yuta Uetake is now working with us, and also some contributors of the collaborators outside, and also the students' photos. And I want to skip that the video because if some of you are interested in the circumstances of our the laboratory, you can go to the homepage and go to the movies. So finally, I want to show again about the Indonesian version of homepage of the QR code. So if you are interested, please go to that homepage. Okay, finally, thank you for your attention. Thank you very much. And sorry for the so much trouble. Thank you very much.
Thank you very much, Professor Sakurai, for your fascinating talks about sumanen synthesis. Also, now we have a question for you. So for the first one comes from Dr. Maria Ulfa from Brawijaya University. She asks about because you have so beautiful structure of sumanen and also their derivatives. What is the promising application of the compounds of sumanen?
Okay, so maybe the most straightforward application is the organic materials for the organic electric materials, because that the sumanen shows the unexpectedly the high N-type conductivity thanks to the ball-shaped structures. So that such kind of the very unique stacking structures it shows a very anisotropic conductive materials. So and also now we are combined with the ball-shaped structures with the graphene, and also shows the very good very high performance of the capacitor. So that means the straightforward application must be the several fields of the organic electronic materials. And another potential application is this ball shape also induce the thermoelectricity. So that means that we can develop the kind of the wearable battery systems by adjusting these kind of the molecules. Because the wearable the battery does not require the high voltage. So of course the sumanen systems cannot get the high voltage, but very effectively convert from the heat to the electrics. So therefore that yes, since the sumanen is an organic compound, so that we really expect that that can be expected to the kind of the wearable thermoelectricity systems. Is it okay?
Okay, Purva. Okay, we have time for one or two more questions from the participants. So please, if you have any questions. Or maybe while we're waiting for one more question, I have a question about the sumanen structure, because you're showing us that sumanen structure is like a ball, and then there's they are aromatic compounds, so they have double bonds, and some of them has single bonds. Does it matter? I mean, the amount of double bonds or single bonds in the sumanen?
Okay, just
Does it related to their characteristic or properties? The double bonds.
Of what? Sorry,
the double bonds in the sumanen.
Okay, so of course, yeah. Okay, I didn't show that some example. The sumanin has totally 1, 2, 3, 4 aromatic rings, and but this is a very highly kind of highly curved, right? Highly curved. So that means the central benzene ring does not show much the aromaticity. So therefore, such kind of the cycloaddition reaction can happen on the center of the benzene ring. So that means that its reactivity is somewhat similar to the reactivity of the C60 or something else. So sometimes the internal carbon shows a very high reactivity. So this is quite different from the usual aromatic compounds reactivity. Yeah, that is a quite unique points of the sumanin, and also that this is a kind of the very difficult point for us, because we tried a very usual transformation of the organic chemistry, but sometimes the sumanin shows a very, very different reactivity. So that is makes a lot of trouble to the student.
Because it's supramolecular chemistry is quite terrifying for student. Okay, I think we have no more question for you, so we can move on to the next speaker. But if you have any question later for Professor Sakurai, for our participant, yes, you can.
I'm a little bit wonder, so that maybe my field is quite not so familiar with the most of the Indonesian students. But maybe my students' talk is much more familiar, so that you can enjoy my students' talk later. Yeah. But anyway, so thank you very much for your tolerance for the waiting to me.
All right, thank you very much once again, Professor Sakurai, for your presentation. Okay, so we now move on for our fourth speaker, Professor Warsito from our university, Brawijaya University. But if you still have a question from Professor Sakurai, you can write down in the chat, and Professor Sakurai maybe will answer your question directly to the chat session.
Okay, thank you for Anna Safitri.
Thank you, Pak Warsito.
Can I share screen for PPT, my PPT?
Yes, Pak. Sure.
Good morning. The Honorable keynote speaker, Prof. Hideki Okamoto, Prof. Mikio Nishizawa, Prof. Hideru Sakurai, and student presenter Sato Tatsuko, Aoi Tatsuki, Andrian, Pat Saratip, and Momodo. Ladies and gentlemen, now my paper is entitled Major Component of Essential Oil is key compound in drug synthesis. We have done this research with postgraduate students from Department of Chemistry, Faculty of Mathematics and Natural Sciences, Brawijaya University. Background in this research, lately, in addition to the what community facing the COVID-19 pandemic, there are also challenges of degenerative disease that tend to increase. Career disease rank second after COVID-19 pandemic. And WHO notes that more than 4.1 million people per year suffer from cancer and 15% die from this disease. So there are two approaches that have been used so far. two approaches in satisfy drug needs. One approach, synthesis from synthetic material from petroleum. Weaknesses of the first approaches, not renewable, and synthetic was is difficult to degrade. And two approaches by herbal drug. Weakness of these approaches are quantity very small of active compound and processing are complicated. So that approaches not effective to drug producing. Approaches alternative we have done by semi-synthetic with component of essential oil, a starting material. Advantages, renewable, available abundance, and biodegradable. Why not component of essential oil? Some of the essential oil we can get from the leaves of plants. For example, Alsinum sanctum, Cinnamomum cassia, Cymbopogon citratus, Mentha piperita, Gaultheria fragrantissima. Another, the major component of essential oil have contain more than 30%. Another, the major component have two or more functional group. For example, eugenol molecule contain phenolic and carbon unsaturated and aromatic ring functional group. So it can undergo esterification reaction for phenolic functional group, addition and oxidation for carbon unsaturated, electrophilic substitution for aromatic rings. Another molecule, example for limonene. In limonene molecule contain unsaturated carbon in cyclic or out cyclic. You see some molecule skeleton of essential oil have potential as starting material in drug synthesis. For example, cinnamaldehyde, eugenol, isoeugenol, methyl eugenol, methyl isoeugenol, limonene, methyl salicylate, geraniol, and citronellol. All molecule skeleton contain two or more functional group. Now, how effective strategy to transformation of major component of essential oil to drug molecule candidate? 5 steps to changing essential oil component into drug molecule candidate. 1 step, designing derived molecule based on the result of reaction with synthetic chemical reagent and combining intermolecular of essential oil. 2 step, screening a drug candidate with docking molecule with autodock 4 using PXPA. 3 step, isolation and purification of major component. And 4 step, perform synthesis or semi-synthesis. And finally, 5 step, EC of drug molecule candidate by Fred-based EC for metric metalloproteinase 9, MMP9, and MTT-EC for T1 cancer cell. In this research, it has been design it by making more than 100 molecules of essential derivative. From iogonal derivative, anetal derivative, limonene derivative, cinnamaldehyde derivative, and salicylic acid derivative. Now, you see this is figure 1. This is figure 1, a protein-based cancer network. And protein used in screening in research have yellow color. Other than MMP9, MMP2, CCNE2, TP53, and VIK1. And other protein involved blue color. Docking molecular in this research based on correlation between protein from breast cancer screening result to cancerous protein. So in this research, breast cancer receptor target other than MMP9, cyclin A2, MMP2, TP53, and VAK1. So, it's breast cancer receptor interaction with ligand and binding affinity as an indicator of protein anti-cancer. So we can compound with anti-cancer potential. And then you see in table 1 to table 5. Table 1 are docking result of anetal derivative. Table 2 docking result of cinnamaldehyde derivative. And table 3 docking result of limonene. And table 4 docking result of iogonal derivative. And table 5 docking result of iogonal derivative. The docking results show that the interaction of the ligand with the cancer promoter receptor protein MMP9 more suitable for all essential derivative than interaction with other receptor protein. And you see some cross combining of essential oil compound have potential as drug candidate. A limonene salicylate number 1 and 2, number 2, cinnamaldehyde salicylate number 3, iogonal salicylate number 4, isoiogonal salicylate number 5, and cinnamaldehyde iogonal number 6, and so on. And this table, result docking from combining of component essential oil. You see, limonene salicylate have binding affinity highest value between another combining of chemical from essential oil. And all cross combining of essential oil has a higher binding affinity value than doxorubicin as control. And then result in silico and in vitro test of derived molecule of essential oil between derived compound rhodinosalicylate have value IC50 in vitro smallest with 1.69 59 and limonene salicylate IC50 in vitro have value 15.13, smallest between combining compound of essential oil. And then conclusion in my research, major component of essential oil have potential starting material in drug synthesis. Number two, derived molecule of cross combination of essential oil compound have high potential as breast cancer drugs. And number three, molecular derived from essential oil such as limonene salicylate, rhodinosalicylate, and echinosalicylate has the potential as candidate for anti-breast cancer drug with IC50 against MMP9 and 41 cancer cell are 23.56 and 15.13 microgram per milliliter, 1.59 and 104.44 microgram per milliliter, and 6.4 and 48.98 microgram per meter respectively. Thank you very much for Ana Safitri.
Thank you, Bapak Professor Warsito, for your interesting talk about essential oil and their biological activities. So now we have discussion session. We have one question for you. For the first one from Dr. Ulfa, Ibu Ulfa. Do you want me to read the question or share the question for you to make it easier? Okay, I read the question for Ibu Ulfa. For Pak Professor Warsito, what do you think about the mixture content in extract? The mixture content of extract, is it give a side effect by induce or reduce the activity of your targeting compound? Or maybe can you get the question, Bapak Warsito?
Yeah.
Maybe I share screen ya for the questions.
Yeah,
This is the question from Ilbu Dr. Ulfa.
Okay. In my research, by combining several essential oil compounds, give different activity of target compound depending on the protein target to induce its activity.
Okay, so the mixture content did not give a side effect. Tidak memberikan
not effect something.
Tidak ada, no give side
yeah.
effect. Okay, that's good to know. Okay, Pak. The next question, we still waiting for the next. The question. Maybe I will check the chat again for the question. Okay, so maybe I will ask Pak Warsito about the activity anti-cancer, because you said that essential oil also has effects as anti-cancer. Is it mixture of essential oil, or when they sendiri-sendiri for the essential oil as anti-cancer, sebagai anti kanker, essential oil? Because usually essential oil is antioxidant or anti-inflammasi, but now it's anti-cancer, sebagai anti kanker. Pak Warsito, you hear me?
It's better to combine compound that one compound. It compound reaction.
Okay. Yes.
Okay.
It's better if the essential oil is in the mixture rather than their isolated compound. Okay. Do we have? Yes.
Yeah. One molecule compound of essential oil and molecule essential oil another reaction to new molecule derivat, not mixed between two molecule compound of essential oil.
Okay. Okay, thank you very much, Bapak Professor Warsito. Oh, we have one more question, the last one, from Professor Mikio Nishizawa. Bapak Warsito, do you have a machine to extract a large amount of essential oil in your university? Do you use HPLC to check the quality?
Yes. I check quality with GCMS.
GCMS.
Yes.
Do you have a machine, big machine in essential oil in Institute Aksiri to extract?
Yes.
Special machine to extract.
Fractionation
Machine.
Apparatus to isolation of one compound.
Okay, so for Professor Nishizawa, Professor Warsito said that because Professor Warsito is also head of Institute Atsiri or Essential Oil Institute. We have Essential Oil Institute in Brawijaya University, and this institute has has complete instruments to extract a large amount of essential oil, like the big one they build by themselves, like customized. Because this institute is obviously working on the research focused on essential oil. And for the detection, Professor Warsito using GCMS. Okay, thank you very much once again, Professor Warsito. So now I conclude this session. So we have come to the final conclusion for this session. Thank you very much for all our keynote speaker, Professor Nishizawa, Professor Warsito, Professor Sakurai, and Professor Okamoto for your great talks. And now I am handing over the session to our MC, Sania. Thank you very much. And thank you to you all to having me as your moderator. Thank you. Good morning.
You, Mrs. Anna, our moderators, for the first session. It was such a blast. We have a lot of unanswered questions, of course, but don't worry for all the participants that the committee will help you to communicate your questions to the keynote speakers, and we will send you the conclusion of our symposium today. And I will also inform you that today's symposium is live on YouTube and it will be saved so that it is accessible for you if you want to reach it out next in the future. So before we proceed to the next session, to the student oral presentation, we will have a 10 minutes break. So please enjoy your coffee, enjoy your meals. In the meantime, see you.
MIPA merupakan salah satu di Universitas Brawijaya yang beranggotakan 5 jurusan, yakni jurusan Matematika, Statistika, Fisika, Biologi, dan jurusan Kimia. Sebagai salah satu jurusan yang berada di bawah naungan Fakultas MIPA, jurusan Kimia telah berdiri sejak tahun 1987 dengan membuka program studi sarjana kimia. Hingga tahun 2020 ini, jurusan Kimia telah mengabdikan dirinya selama 33 tahun. Dalam kurun waktu tersebut, jurusan Kimia telah berproses dan berhasil mengembangkan diri, sehingga saat ini memiliki 3 program studi, yaitu program studi sarjana kimia yang telah mendapatkan peringkat A oleh Badan Akreditasi Nasional Perguruan Tinggi atau BANPT, dan program pasca sarjana yang terdiri dari program studi magister kimia dan doktor kimia.
Nama saya Dr. Masruri, saya Ketua Jurusan Kimia Universitas Brawijaya. Jurusan Kimia mempunyai visi menjadi lembaga terkemuka di bidang pendidikan dan riset kimia yang berwawasan lingkungan, riset pendidikan dan riset kimia dalam mengembangkan sumber daya alam yang berwawasan lingkungan. Jurusan Kimia juga mempunyai misi, ada 3 misi yang diemban dari visi tersebut, yaitu yang pertama adalah misi pendidikan untuk menghasilkan lulusan bidang kimia yang profesional dan diakui oleh masyarakat nasional maupun internasional. Misi dalam mengembangkan riset-riset yang berbasis bahan alam lokal untuk menjadi produk unggulan, dan misi yang ketiga adalah mengimplementasikan hasil-hasil riset yang telah diperoleh pada tahap sebelumnya yang dapat digunakan untuk mendukung industri, pengembangan industri yang berwawasan lingkungan.
Perkenalkan, nama saya Dr. Ika Oktavia Wulandari. Di sini saya selaku staf pengajar dosen di jurusan Kimia Universitas Brawijaya. Jurusan Kimia Universitas Brawijaya telah memiliki sumber daya manusia staf pengajar dosen yang sangat profesional dan kompeten di bidangnya masing-masing. Mayoritas dosen di jurusan Kimia Universitas Brawijaya bergelar doktor dan profesor. Selain itu, dosen-dosen di sini juga berasal dari universitas ternama baik di dalam maupun di luar negeri, seperti Jepang, Jerman, dan Australia. Staf pengajar dosen juga telah memiliki riset pengembangan yang terarah, sehingga dapat memberikan fasilitas yang memadai bagi mahasiswa untuk pengembangan penelitiannya.
Belajar mengajar itu sangat baik, fasilitasnya juga baik, dari segi dosen-dosennya itu sangat baik, bisa memfasilitasi baik menggunakan bahasa Indonesia dengan bahasa Inggris. Suasana dalam ruang kelas juga sangat baik karena jumlah mahasiswa di dalam ruang kelas itu dibatasi sedemikian rupa sehingga tidak terlalu desak-desakan, dan untuk memahami materi itu baik sekali. Kemudian untuk minat bakatnya sendiri, untuk jurusan kimia itu ada himpunan yang dinamai dengan HMK atau Himpunan Mahasiswa Kimia, di mana di himpunan tersebut memfasilitasi minat-minat dari mahasiswa kimia. Ada berbagai macam divisi seperti LBI, LBO, dan lain sebagainya. Kemudian untuk di tingkat fakultas terdapat eksekutif mahasiswa, badan legislatif dengan nama DPM, dan LOF yang banyak sekali menampung minat dan bakat dari mahasiswanya. Kemudian untuk di tingkat universitas sendiri terdapat banyak sekali organisasi seperti EM, UKM, dan lain sebagainya, sehingga untuk minat bakat dari setiap mahasiswa itu dapat terwadai baik di lingkungan jurusan, fakultas, dan universitas.
Pada saat kita belajar di dalam kelas, kita tidak hanya mengetahui ilmu-ilmu yang kita dapatkan, tetapi kita bisa mengeksperimenkan atau mengimplementasikan ilmu-ilmu yang kita dapatkan di laboratorium. Jurusan kimia sendiri memiliki berbagai macam laboratorium yang didukung dengan berbagai macam instrumen-instrumen yang sangat baik. Seperti contohnya ada laboratorium biokimia, laboratorium fisik, kemudian laboratorium anorganik, analitik, dan juga organik. Kita semua tidak khawatir bagaimana prospek kerja pada saat lulus berkuliah. Buat teman-teman semua, jangan khawatir, karena pada saat lulus berkuliah dari jurusan kimia Universitas Brawijaya, banyak prospek-prospek yang ditawarkan, seperti pada industri makanan, farmasi, ataupun industri yang lainnya, dengan berbagai macam posisi seperti quality assurance, quality control, research and development, kemudian analis laboratorium.
Saya Zubaidah Ningsih AS selaku koordinator kemahasiswaan dan alumni di jurusan kimia FTP MIPA Universitas Brawijaya. Tanggung jawab yang saya lakukan adalah untuk meningkatkan suasana akademik di jurusan kimia. Suasana akademik ini bertujuan untuk meningkatkan interaksi antara dosen dan mahasiswa di luar kegiatan perkuliahan. Kegiatan-kegiatan yang dilakukan untuk meningkatkan suasana akademik ini diantaranya adalah penelitian yang dilakukan oleh dosen dan mahasiswa, kemudian juga pengembangan program.
Okay, I think that our 10 minutes break is over. So we will proceed to the second session, which we have student oral presentations. And for the second session's leader or moderator will be Mrs. Siti Maria Ulfa, Doctor of Science. I put my trust on you. Please, time is yours.
Okay, thank you very much, Sania. Welcome again to all of the participant, presenter, and also maybe the keynote speaker who's still in this room. So now we're moving to the student symposium. We have 5 presenters from Brawijaya University, Osaka University, Ritsumeikan University, and also from Okayama University. So for the first presenter, we have Andrian Sucahyo from Brawijaya University. He is a magister student from Department of Chemistry, Faculty of Science. His presentation is about the anti-inflammatory and antioxidant analysis of Caesalpinia sappan hardwood extract using in vitro and in silico methods. The presentation time and also discussion should be 15 minutes, so you can present 10 or 12 minutes for presentation, and then question and answer around 5 or 3 minutes. Please, Andrian, time is yours. Andrian's in here?
Can I share screen my
presentation? Yes, please.
Is it fine?
Still process. Okay, it's clearly in the slide.
Okay. Can I start now? Yeah.
Yes, please.
Okay. Thank you for the opportunity for today. My name is Andrian Sucahyo. Today I will present my research about anti-inflammatory and antioxidant analysis of Caesalpinia sappan hardwood extract using in vitro and in silico methods. So for the outline for today's presentation are introduction, methods, results, including extraction and partition, phytochemical screening, antioxidant and anti-inflammatory of Caesalpinia sappan fractions, fractionation, activities of Caesalpinia sappan subfractions, LCMS, and docking. The other final 2 are result and next research plan. So for the first one is introduction. As you may already know that oxidative stress can lead to inflammation by the activation of NF-kappa B or releasing cytokines or chemokines. Conversely, inflammation also can cause the oxidative stress. So those 2 events will create a continuous cycle. So we need a compound that could act as an antioxidant and anti-inflammatory agent. The picture on your right is Caesalpinia sapan herbal extract, and it has analgesic, antioxidant, anti-diabetes, anti-inflammatory, antimicrobial, and anti-cancer activities. This slide is about known compounds that have been isolated and elucidated from this plant. And on the middle of your screen is flavonoid framework, and the outer part are the example of flavonoids. Flavonoid is the major compound found in the Caesalpinia sapan extract, but I couldn't include all of the flavonoids example because of the time limitation. 5 compounds that have been analyzed for their activities are brasilin, protosaponin B, sapanol, protosaponin C, episapanol. From all of those compounds, brasilin has the highest anti-inflammatory activities by inhibiting IL-1B. IL-1B is pro-inflammatory cytokines that can induce inflammation. It inhibits at 18 micromolar, but it's still higher than IL-1B. I mean dexamethasone. Dexamethasone is a drug for curing inflammation. So we need to find another compound in this plant that could suppress the activity of dexamethasone. So for our research, we were using extraction, partition, phytochemical screening, fractionation, antioxidant and anti-inflammatory assay, LCMS, and docking methods. From extraction and partition, we extracted Caesalpinia sapan herbwood with methanol solvent. From there, we get the crude methanol extract, and then we partitioned with 3 solvents. The first one is ethyl acetate soluble fraction, fraction A, fraction B, and butanol soluble fraction. And the last one is fraction C, water-soluble fraction. It is similar to Prof. Nishizawa methods. And from phytochemical screening here, this table will show you that flavonoids are present in all of the fractions from methanol, ethyl acetate, butanol, and water. Not only flavonoids, but saponin and steroid also present in all of them. So we're moving to the antioxidant and anti-inflammatory activities of Caesalpinia sapan. From the figure on your left is antioxidant activities of Caesalpinia sapan fraction. In this case, ethyl acetate fraction Fa has the highest antioxidant activities compared to Fb and Fc. Also, it is lower than ascorbic acid as a positive control. How about the anti-inflammatory activities? From this case, we also found out that fraction A, ethyl acetate fraction, has the highest anti-inflammatory activities compared to fraction B. This is figure about suppressing NO production caused by LPS. In this case, LPS induces the inflammation by the production of nitric oxide. So we are giving fraction A to the cell, and we found out that when we are giving 7.5 microgram per milli, we found out that it decreased from 60 to 52, and about 15 microgram per milli, it decreased significantly. So it is a concentration dependent. So we need to further purify fraction A because this is the most active fraction. And we purified using silica gel chromatography using the combination of solvent, chloroform, and ethyl acetate. And we got 9 subfractions in here. And from those subfractions, we analyzed the antioxidant and anti-inflammatory activities of those. And we found out from antioxidant activities using DBPH that A3 until A7 have better antioxidant activities with lower IC50 than ascorbic acid as a positive control. How about the anti-inflammatory activities? In here, you can see that inside the red box is A6. In this case, A6 almost suppress the production of NO almost zero. So it is the subfraction are effective or the compound contained in this subfraction is cytotoxic. So we need to find out using WST analysis to find out the cytotoxic effect of this subfraction. And we found out that ASIC is toxic to the raw 264.7 cell. So it couldn't produce any nitric oxide because the cell is dead. So we need to find another subfraction that show a promising result. In this case, A3 and A7 shows a promising result as suppressing NO production induced by LPS. And again, A3 and A7 also concentration dependent. So we need to find out what compound or the major compound contained in A3 and A7. From A3, we found out that pinostropin is the major compound in A3. It is a flavonoid compound. The A7 major compound is boreol. It is also flavonoid derivative flavonone. So from all of them, 4 are flavonoids. But the last one, alternaryl methyl ether, is polyketide. So the major compound found in this plant are flavonoids. So this table will show you that not only flavonoids are present in this plant, there are also some polyketide, anthraquinone, heterocyclic compound, coumarin, fatty acid, steroids, and phthalate. And the last slide is docking against anti-inflammatory receptors. And we only use molecular docking to predict what compound exert the best anti-inflammatory activities, but we cannot say 100% sure that this compound has the highest anti-inflammatory activities. So we using molecular docking to iNOS receptor. iNOS receptor is responsible for producing nitric oxide by converting arginine to citrulline. So we need to find a compound that could inhibit the active site of iNOS enzyme. So it could possibly inhibit or reduce the production of NO caused by iNOS enzyme. So in this case, co-crystal ligand DB07388 had been designed specifically for inhibiting the active site of iNOS enzyme. And it has binding energy of minus 8.26. How about pinostropin, that the compound that we isolated from this plant? It also has similar binding energy, but higher inhibition constant. So how this compound able to have similar binding energy like the co-crystal ligand? So we need to find out in the next slide. So in this slide, as you can see, the background, the colorful background is the active site or the pocket of the iNOS enzyme. So the co-crystal ligand, namely DB07388, as you can see here, it is perfectly fit the active site of this enzyme adjacent to the heme. Heme is also important in converting arginine to citrulline. So if the co-crystal ligand perfectly fit this enzyme pocket, then it selectively inhibit and could significantly decrease the production of NO. So how about pinostropin? As you can see in here, pinostropin also has similar location within the active site of this enzyme. So it might have similar activities like the co-crystal ligand. How about hydroxybrasilin? Hydroxybrasilin has higher binding energy. How? Because hydroxybrasilin, as you can see here, it has 4 rings and the structure is larger. So it couldn't fit properly into the active site of this enzyme. That's why it couldn't selectively inhibit the active site of this enzyme. So for the conclusion, Caesalpiniasapan heartwood extract shows a promising result as an antioxidant and anti-inflammatory agent. The numerous flavonoid compounds when found in the Fa subfractions contribute to their antioxidant activities. Anti-inflammatory activities of A3 and A7 shows a promising result by suppressing NO production using raw 264.7 cell-induced by lipopolysaccharide. For using in silico method, we could see that pinostropin has the best binding energy and similarity to the co-crystalline ligand when docked against inos receptor. Also, Poriol has the same similarity with pinostropin and the co-crystalline ligand, but I couldn't include it in this presentation because of the time limit. So for the next research plan, we would love to purificate the constituent in the Fa subfraction, maybe Poriol because of its limited data, and currently we are doing animal experiment using diabetes mellitus type 2 mice model. And thank you for Brawijaya University and Ritsumeikan University for funding this research. That's it from me. Thank you very much for the opportunity.
Okay, thank you very much, Andrian, for the nice presentation. And now we move to the question and answer session. In the chat room, there is several questions from Nishizawa Sensei. Dear Andrian, for which disease C-Sapan, Caesalpinia Sapan heartwood is used? Does it effective the disease other than inflammatory disease?
Yeah, it also able to act as an antioxidant, anti-cancer, I will show you in the first presentation, first slide. Here, it also can act as an analgesic, antioxidant, anti-diabetes, anti-inflammatory, antimicrobial, and anti-cancer activities. So commonly, Indonesian people use Caesalpinia sapan to combine it with their food and beverage, and it usually to cure anti-cancer, to cure anti-diabetes, to cure diabetes.
Oh, okay, thank you very much. Maybe we can chat later with Professor Nishizawa. And then one question from Ferry. Did you targeted the active site of inos enzyme in the molecular docking steps, or you dock it blindly and tested whether the compound will attach freely in the preferable area of inos? Also, I suggest you to test it on the molecular dynamics to see whether the interaction is stable or not. Thank you. What's your comment, Adrian?
Okay, thank you for the question. So my method is directly dock my compound to the active site of this enzyme because the co-crystalline ligand already sit into this active site. So I just use the compound that we isolated from this plant, namely pinostropin, with the same location as the co-crystalline ligand. So it directly inhibit this active site. So how about the suggestion? Thank you very much for your suggestion. I will try it in the future work. Thank you very much.
Okay. Thank you very much for the answer and for the presentation, Adrian, because the time is very limited. And now we can give applause to Adrian for his presentation. Now we are moving to the next presenter from, thank you very much, Adrian.
Thank you very much.
Okay, now we are moving to the next presenter from Ritsumeikan University. The presentation title is Anti-Inflammatory Effect of Furanokumarin from the Root of Angelica daurica. The presenter is Sato, Tatsuki Sato. I know him well. He's very nice guy. Sato is in here?
Yes, I'm here.
Okay. Please, Sato, present your research. Time is yours.
Okay, thank you for my introduction. Can everyone see my slide?
Yes, I think it's okay. You can start now.
I'd like to start my presentation. Okay, my name is Tatsuki Sato. I'm in Ritsumeikan University in Japan. Today, I'd like to present our research about the anti-inflammatory effects of fluorocumarins from the roots of Angelica dafrica. The root of Angelica dafrica, RAD, has been traditionally used for inflammatory skin diseases, such as atopic dermatitis. RAD contains fluorocumarins such as imperatolin and viacamglycol and monoterpenes such as alpha-pinene, camphene, and verapidine. The methanol extract of RAD has been reported to suppress production of inflammatory mediators, nitric oxide NO, and prostaglandin E2 in lipopolysaccharide-induced mouse macrophages. However, there have been few reports about its anti-inflammatory effects. Here, we searched for the compounds of RAD which suppress production of NO. We extracted the root of Angelica dafrica, RAD, with methanol and evaporated under reduced pressure to obtain methanol extract. The methanol extract was fractionated into 3 fractions based on the hydrophobicity: ethyl acetate layer, fraction A, and butanol layer, fraction B, and aqueous layer, fraction C, was obtained respectively. The proportions of the fractions by total solid weight were 12.1% fraction A, 8.1% fraction B, and 79.8% fraction C. To check the anti-inflammatory effects of each fraction, we prepared the primary cultured rat hepatocytes. Hepatocytes were isolated from the liver of male Wistar rat by collagenase perfusion. The hepatocytes were incubated at 37 degrees and 5% CO2 overnight. In the next day, the hepatocytes were treated with iron beta to induce NO production and with different concentrations of each RAD fraction and constituents. After 8 hours incubation, the level of nitric oxide in the medium was measured by Gris method. To monitor the cytotoxicity, we measured the activity of lactate dehydrogenase, LDH. Furthermore, we also analyzed the expression of inducible nitric oxide synthase, iNOS protein, by Western blot analysis. To assess the anti-inflammatory effect of crude fractions of RAD, a nitric oxide assay was performed. Please look at this figure. Compared to iron beta alone, fractions A and B suppress nitric oxide production dose-dependently, whereas fraction C didn't suppress nitric oxide production, and fraction A, B, and C didn't show cytotoxicity. Next, we checked the iNOS protein expression of fraction A, B, and C from the RAD extract. Compared to the iron beta alone, fraction A and B dose-dependently decrease the iNOS protein expression here. And whereas fraction C did not decrease the iNOS protein expression. These results indicated that fraction A and B suppress nitric oxide production by decreasing the iNOS protein expression. The activity of fraction A was stronger than fraction B, so we separated fraction A to isolate active constituent. To isolate the principal constituents in fraction A, we performed silica gel column chromatography using N-hexane and ethyl acetate based on the polarity, then obtained 12 subfractions. We isolated AD1 from A2 from and AD2 from A7 and AD1 and AD2 performed NMR. The spectra of AD1 was corresponded to that of isoimperatorine, and AD2 was corresponded to that of oxypoisidine. And to check the activity in each subfraction, we measured NO production in hepatocytes. Compared to fraction A, our data indicated that subfractions A3, 4, and A5 more suppress the NO production than fraction A. This result indicated that principal constituents may be included in subfraction A3, A4, and A5. A3 to A5 showed the same spot patterns in pin layer chromatography. Then, in order to separate A5, we performed two preparative HPLC and obtained 4 subfractions. And we isolated AD3 and AD4 and performed NMR. The spectra of AD3 was corresponded to that of imperatorin, and AD4 was corresponded to that of pheropterin. In addition, we were interested in A9 because the amount of this subfraction is large. In order to separate A9, we performed preparative TLC and isolated AD5. The spectra of AD5 was corresponded to that of oxypoisidine methanolate. And interestingly, pheropterin and oxypoisidine methanolate suppress NO production and inosprotein expression, although other compounds didn't suppress NO production. Look at this figure. Compared to I1 beta alone, pheropterin and oxypoisidine methanolate suppressed nitric oxide production dose-dependently without cytotoxicity. Next, we checked the inosprotein expression of pheropterin and oxypoisidine methanolate compared to the I1 beta alone. Then they decrease the inosprotein expression dose-dependently. In addition, we investigated the mechanisms of anti-inflammatory effect of pheropterin and oxypoisidine methanolate using qRT-PCR analysis of inos and TNF-alpha, tumor necrosis factor alpha messenger RNA. Compared to I1 beta alone, pheropterin and oxypoisidine methanolate suppress inos and TNF-alpha messenger RNAs in hepatocyte. Next, HPLC analysis was performed to estimate the content of each constituent in fraction A. The contents of isoimperatorine and imperatorin were higher in fraction A than the other constituents. This table shows the summary of constituents isolated from the Angelica d'Africa root. Particularly, the contents of pheropterin was higher than oxypoisidine methanolate. Okay, this is summary and discussion of this study. And the methanol extract of RAD was fractionated into fraction A, fraction B, and fraction C. And fraction A and B suppressed both of NO production and inos expression. The activity of fraction A was the strongest of 3 fractions. And ferropterin and oxypoisogen methanol decreased NO production and the expression of inosine protein. And ferropterin and oxypoisogen methanol decrease the levels of inosine and TNF-alpha messenger RNA. The content of ferropterin was higher than oxypoisogen methanol. Therefore, ferropterin and oxypoisogen methanol may be responsible for the anti-inflammatory activity of the root of Angelica dafrica by suppressing inosine and TNF-alpha gene expressions. That's all for my presentation. Thank you for listening.
Thank you very much, Sato-san, for your nice presentations. We have now moving to the answer and question sessions. There are 2 questions from you for you. The one, which one? What kind of disease that can be cured by this herb? From Christoph John.
Okay. This herb has been reported to cure skin diseases such as atopic dermatitis. And also this herb contained in camphor drugs. So these constituents maybe cure skin diseases. Thank you.
Okay, so it can cure skin disease, I think. And then the second question from Dr. Anna. Do you think that other parts of the plant, Angelica dahurica, will give different efficacy as anti-inflammation or not?
Okay.
So you also can check in the chat room for the questions.
Yes, I'll check.
From Dr. Anna. And the last question, I think from Dinia-san, from your standby.
Okay, I find it. Different efficiency. I think we only measure NO production to assess anti-inflammatory, but yeah, and I measured TNF-alpha with using qRT-PCR. So not only skin diseases, maybe I think and not only dermatitis but also diabetic mellitus and so on. So yes, I think this herb may cure such as diseases.
How about the other part of the Angelica dahurica? You use the root, I think. The root of.
Angelica dahurica.
And how about another
different herb, another plant. Okay, I'm studying Peonius saffruticus, and this herb Peonius saffruticus and cure cardiovascular diseases. So not only skin diseases and yes, cure anti-inflammatory disease.
Okay. I know that Nishizawa Sensei Laboratory have many have tried to isolate active compound from different part of the campo medicine, such as for example, for Dinia from the fruits, and another one Li Sang, I think, from the bud, and etc. So thank you very much, Sato. And I think the last question from Dinia Sang: do you think this plant also has anti-diabetic effect? Because previously in bitter melon has anti-inflammatory and also anti-diabetic as well. So I think this is the last question.
My answer is I have no idea because this plant Angelica d'Africa not didn't measure in OB or adipocytes. So yes, so in the future, and we check in adipocyte to assess anti-diabetic effect. Thank you.
Okay, thank you very much, Sato. Please give applause to Sato, and thank you for the nice presentations. Okay, next we move to the next agenda. We have Aoi Tatsuki-san. It's similar name with Sato from Okayama University. Are you here, Tatsuki-san? Another Tatsuki.
I'm here.
Okay, she will present her research about the excited state intramolecular proton transfer, ESIPT fluorescence of thalamid having acyclic and cyclic sulfonamide moieties as the proton donor. Please, time is yours, Ms. Tatsuki.
Can you see my slide?
Yes, we can see your slide well, and also your voice is here clearly here.
Thank you for kind introduction. Today I'll introduce ESIPT fluorescence compound. First, I'll explain excited state intramolecular proton transfer, ESIPT. ESIPT is a photochemical process through which the corresponding electrically excited tautomer form is produced. ESIPT fluorescence emits from excited tautomer form. The fluorescence observed with very large stroke shift because the forms which absorbs light and emit fluorescence are different. In addition, ground state intramolecular proton transfer, GSIPT, is a process that returns from ground state of tautomer form to that of original form. Fluorophores which got back to original form to that of original form through GSIPT are excited again and emit ESIPT fluorescence. Fluorescence behavior of ESIPT fluorescence is sensitive to various external stimuli, and they have been applied in various fields such as chemical sensors, bioprobes, and display materials. ESIPT fluorophores possess a proton donor and acceptor. Most conventional ESIPT fluorophores have an OH functionality as proton donor. Although an NH functionality can be an alternative or OH1, there are much fewer studies on ESIPT fluorophores having an NH proton donor. With OH type ESIPT fluorophores, one can manipulate the ESIPT fluorescence properties by change of chromophore structure. With NH type ESIPT fluorophores, one can easily manipulate the ESIPT fluorescence properties by chemical modification on the nitrogen atom. We found that phthalimide derivatives display ESIPT fluorescence for which the NH part of the sulfonamide and amide carbonyl moiety respectively served as proton donor and acceptor. In our previous study, we found that ESIPT fluorescence properties are manipulated by change of substituents. In this study, ESIPT fluorescence properties of the amido substituted phthalimide derivatives having an acyclic and cyclic structure were investigated. First, I'll explain about synthesis of compounds 1 and 2. Acyclic compound 1 was synthesized by deriving 3-amino N-propyl phthalimide from 3-methyl anhydride and reacting with the corresponding sulfonate. Cyclic compound 2 was cyclized using tensile butyl nitride after reacting with 3-amino N-propyl phthalimide with orthonitrobenzene sulfonyl chloride to reduce the nitro group. Next, the ESIPT fluorescence properties of obtained compounds were observed. These are absorption and fluorescence spectra of compounds 1 and 2 in toluene. In no-polar solvent, compound 1 shows absorption band at 341 nanometer and fluorescence band at 611 nanometer. It shows very large Stokes shift, 12,600 centimeter -1, and the fluorescence band assigned ESIPT emission. Compound 2 shows a weak fluorescence band at 425 nanometer and stronger fluorescence band at 645 nanometer. The 425 nanometer fluorescence band can be assigned to the normal amide form of compound 2. The 645 nanometer fluorescence band shows very large Stokes shift, 13,100 centimeter -1, and it assigned ESIPT emission band of compound 2. Therefore, compound 1 displayed only ESIPT emission band. In contrast, compound 2 displayed dual emission from the normal form and the tautomar form formed through the ESIPT process. Next, we investigated solvent effects on the fluorescence spectra of compound 1 and 2. In polar aprotic solvent acetonitrile, compounds 1 and 2 showed blue-shifted emission band compound compared to ESIPT fluorescence. Compound 1 shows ESIPT fluorescence band at 594 nanometer and a little blue-shifted. And compound 2 in acetonitrile shows weak fluorescence. Compound 2 shows ESIPT fluorescence band at 624 nanometer. Compound 1 in acetometer shows weak fluorescence band at 495 nanometer, and it can be assigned to the deprotonated form of compound 1. In polar protic solvent ethanol, compound 1 shows blue-shifted emission band. Compound 2 didn't show fluorescence through ESIPT, but from deprotonated form emission. To confirm the deprotonation effects, the fluorescence spectra of compound 1 and 2 were observed in the presence of a base. Both compounds 1 and 2 showed that absorbance of amido decreased and that of deprotonated form amidate increased. In the presence of base, compound 1 showed that fluorescence intensity or emission from amidate and showed amidate increased and the fluorescence band from ESIPT process disappeared. On the other hand, compound 2 showed one fluorescence band assigned to amidate, and in the presence of the base, the intensity of the band increased. The observed protonation behavior is further supported by proton NMR spectra. Compound 2 displayed NH signal in more downfield shifted region compared to compound 1, suggesting that compound 2 is more acidic than compound 1. These pictures show observed fluorescence of compound 1 and 2. Both compounds show reddish fluorescence in toluene. In acetometry, we can observe yellowish fluorescence. Even if the straight state, we can observe ESIPT fluorescence from compound 1 and 2. In summary, we found that the titrophthalate image shows ESIPT fluorescence properties. In non-polar solvent, both compounds showed fluorescence through ESIPT mechanism. On the other hand, in polar solvent, amidate ion is produced and compound 2 emit amidate emission on a priority basis. Thank you for your kind attention.
Thank you very much, Ms. Aoi Tatsuki-san, for the nice presentations. And you showed to us a different color from each structure. It's very interesting. Now we move to the answer and question sessions. I wrote one question in the chat room, so maybe another participant also can ask later. So I want to ask you, which one is more promising between OH type or NH type substituent produce fluorescence properties? In your first or second slide, you explain to us about OH type and NH type. Yes, in this slide.
So I promise NH type fluorescence and ESIPT. I want to fluorescence having large Stokes shift. So and NH type can easily change color by changing the substituent. So NH type, I want NH type fluorescence.
Okay, thank you. So do you mean that the NH type is more perspective to give a fluorophore compared to OH type?
So OH type, if when we manipulate fluorophore, ESIPT fluorophore fluorescence. OH type is change chromophore structure, but NH type is changing the substituent. Only change substituent. We can change fluorescence wavelength.
Okay, thank you very much. Next question comes from Sania. Maybe Sania can ask directly so we can hear your voice. Please, Sania.
Okay, thank you very much, Mrs. Ulfa. For Aitatsuki-san, you explained that your molecule has a solvent-dependent fluorescence activity, right? So I want to ask you, does hydrogen interaction has any correlation to the solvent-dependent fluorescence, or what kind of solvent give the best intensity for the fluorescent molecule? Is it the more polar one that gives the best intensity, or the vice versa? I think that's all.
Thank you, Sania. Mr. Tsuki also can check the questions in the chat room. So maybe you can answer that questions. So does the hydrogen interaction or hydrogen bonding has any correlation to the solvent-dependent fluorescence? Since when you change your solvent, the fluorescence color become different.
So maybe if there are any other factors that influence the solvent dependence, maybe you can also explain about it. It's okay. I just want to know the backgrounds of the solvent dependence of the fluorescence activity.
Hydrogen. The first question is hydrogen interaction has a correlation to solvent. And the best intensity fluorescence is ethanol. Monopolar solvent, amidate ion emit. So amidate ion emit stronger than USIPT fluorescence. So in polar solvent, intensity of fluorescence is higher.
Thank you very much for your answer.
Thank you.
Okay. Thank you very much, Ms. Aoi Tatsuki, for the nice presentation. And please give applause to Ms. Tatsuki. And we now move to the next presenter from Osaka University. Ms. Butsaratip Suwatananuruk. I'm sorry if I missed the spelling. And his title is Intramolecular Cycloamination of Primary Amines using gold nanoparticles deposited on citric acid modified surface fibrillated cellulose. Ms. Butsaratip, are you here with us?
Yeah.
Okay. Yes, please. Time is yours. 15-minute presentation and also discussion. Yes, please.
For greeting to you all. So my name is can I start now?
Okay, time is yours.
Okay. So greeting to you all. My name is Pusratip Suwatananulak. You can call me Pete just for short. So today I'm going to present the presentation study entitled Intermolecular Cycloamination of Primary amine using gold nanoparticle deposited on fibrillated citric acid modified cellulose. Biomolecule stabilized gold nanoparticle has known as it higher catalytic activity rather than gold nanoparticle itself. The merit of biomolecule is not limited to stabilize the gold nanoparticle. It can also increase the catalytic activity, selectivity, and biocompatibility. There are many types of biomolecule as shown here. Each type serves different purpose and different in catalytic activity. For example, the reaction of homocoupling of phenolboronic acid.
Your side doesn't move.
Sorry. Okay. Sorry, where were I? Okay. So, I talking about the example of homocoupling of the phenolboronic acid. So I will continue from here. So as shown in this reaction, it was shown that chitosan co-stabilized by chitosan show higher catalytic activity rather than on PVP because of the low form hydroxyl group that can activate the substrate and the presence of amine group that can give extra stabilization of gold nanoparticle. So in this case, the functional group play an important role to regulating the catalytic activity of gold nanoparticle. So in this time, we should fibrillated citric acid modified surface cellulose or FCAT as a solid support because the functional group of this one is an acid different from the base that found in chitosan, which might lead to new catalytic property. This material also very easy to prepare and show high resistance for organic solvent. high surface area which perceived as a good property for solid support. The presence of carboxylic group provide an ability to immobilize metal ion. Moreover, it can serve as a solid bond-state acid, and this persistence make it possible to be a heterogeneous catalyst. All the merit of this material make it interesting in using this material as a solid support. In the previous work, they have already proposed the method to synthesize different sites of gold stabilized by PVP or polyvinyl pyrrolidone and transfer from PVP to stabilize by FCAT with efficiency up to 90% without changing the size of gold nanoparticle. This method called time deposition method. Our previous laboratory also studied the catalytic activity toward oxidation of indinol to inanone, show a high percentage of product and also the reusability. Thus, we interesting to expand the application of FCAT to other type of organic transformation. As the oxidation of indinol to inanone, this reaction was proceed with the need of base. However, the citric on the surface can serve as a solid bond-state acid. So base is consumed by the neutralization of solid support. That's why large amount of base was required to proceed this reaction. There is no use to let it perform catalytic activity in base. So we search to other reaction that can proceed in acid or slightly acid condition instead. So we found hydroamination reaction. In this reaction, it can form CN bond with high atomic economy, which really important intermediate in pharmaceutical. For example, in the generation of corneine, which used in pain relief without additive, the addictive side effect. However, the hydroamination reaction are empirically negative. Thus, the catalyst is required to proceed the reaction. Our laboratory already published the hydroamination reaction proceed in slightly acid condition as buffer pH4 was found to accelerate the reaction, and the presence of formyl group can enhance the reaction to obtain 94% yield. Thus, in our hypothesis, we thought that maybe FCAT might work as a reducing agent instead of formic acid, and it might work as an acid salt instead of buffer. So in this reaction, we might successful to utilize the benefit of solid bond-state acid and make this catalyst as a bifunctional catalytic activity. So we start from preparing of FCAT. The cellulose was dispersed in distilled water. Then citric acid was added to disperse and mixture was stirred for 5 minutes at room temperature. The mixture was transferred to heat resistant dish and incubated in oven 130 degrees for 13 hours. After cooling, we transfer the FCAT and put in the water and wash the residual citric acid, removed by water until pH was approximately 7. After that, modified cellulose was successfully washed with methanol and acetone and dry under vacuum to give FCAT as a colorless powder. Then FCAT powder was dispersed in water again and adjusted to pH 9 with sodium hydroxide. The residue was washed with water again to pH 7 before fibrated by dressing mixer, and then it was feed dried for 2 days. Finally, we can obtain the FCAT powder. After get FCAT powder, the gold FCAT was synthesized by adding FCAT with gold PVP into ethanol and adjust pH to 4 for 90 minutes. Then wash catalyst with ethanol for 3 times by centrifugation. The powder was dyed in the vacuum at 40 degrees overnight to obtain gold FCAT. Then it was used in the reaction. So first, we tried this reaction without additional of acid and base. However, we found that when the reaction is not proceed, which means that citric acid on FCAT cannot work as a reducing agent. However, when we add formic acid, we get the product up to 99%. And we cannot find other byproduct compared to the previous results. We also optimize the condition for the reaction. then FCAT can achieve the product up to 99% in 12 hours with only 2% of gold. However, we found the gold reaching out to the supernatant after the reaction. We analyzed it by inducively coupled plasma mass spectrometer or ICP. The result indicate that the concentration of gold reaching out up to 45%. In order to avoid the leaching of the gold, we have to avoid the water, since it was found in the previous research that water can cause severe leaching of gold. So first, we change the mixture of pH4 buffer and ethanol to only pure ethanol, and we found that the leaching of gold was suppressed to 25%. Then we try to get rid of all of the water out of the reaction. We change the aqueous reducing agent to solid form. And we found that the leaching of gold finally was unable to detect by ICP. We also optimized the condition reaction and found that the reaction was proceed in 0.5 atom% of gold in 3 hours without the leaching of the gold. So in this case, citric acid on FCAT might work as an acid source instead of buffer. That's why the absence of the buffer is possible. Significantly increase of reaction rate in pure ethanol might also affect from the changing of gold nanoparticle size during the reaction. From the TEM result, gold FCAT after reaction with mixture of pH4 buffer and ethanol increased dramatically from 1.7 nanometer to 5.7 nanometer, while in the case of using only pure ethanol, particle size of gold nanoparticle is slightly changed after the reaction. Then we check the size dependence of gold nanoparticle. So we study dependent size toward this reaction by using freshly prepared gold FCAT with 1.7, 4.9, and 8.2 nanometer of gold nanoparticle. The yield with the gold nanoparticle size 4.9 is reduced to 29% in 3 hours. And in the case of 8.2 of gold nanoparticle, the product piece is not even observed. Thus, we can conclude that the reaction rate depends on the size of gold nanoparticle. After we get the optimization condition, we try this optimization condition with gold PVP to compare catalytic activity, and we found that the catalytic activity of gold PVP is lower than gold FCAT in 2 hour reaction. As you can see here, the gold FCAT reaching product up to 85%, while in the case of gold PVP is only 45%. And finally, gold FCAT within 3 hours, we can proceed the reaction with 99% yield. We also tie the reaction with other primary amide when we introduce one methyl group on R1. The reaction still occurs perfectly in 4 hours. However, when 2 methyl group was introduced in R2 and RT, the reaction is not proceed. This is due to the steric effect. Unlike in the case of cationic gold complex, these reaction conditions are likely to be more sensitive to steric factor in the case of gold nanoparticle, since there are gold species adjacent to cationic gold site active by oxygen. Therefore, the reaction condition using gold FCAT allow the hydroamination reaction to perform in a terminal alkene selective manner. Good example to show this effect is the cyclization of amide having both allyl group and penyl group. We found that the cyclization occurs selectively at allyl group to give this product up to 99% without cyclization product of amide with penyl group. So this leads to my conclusion. The intermolecular hydroamination reaction proceeds in the absence of buffer pH4. By using gold FCAT, the reaction rate affected by the size of gold nanoparticle, and the reaction can proceed with only 0.5 atom of gold. And finally, this catalyst provides catalytic activity selectively with terminal alkene. Finally, I would like to thank all of my support, Sakurai Sensei and laboratory member and others. So thank you very much for your kind attention. So now I would like to answer the question that you may have.
Okay, thank you very much, Ms. Pete from Osaka University. I have one question, a simple question, I think. Is it possible to use your material, FCAC, as a metal adsorbent?
Sorry, can you say that again?
Maybe you can check in the chat room. I write my question in there also.
As a material absorbent?
Yes. Is it possible?
Like, what kind of metal? So, in order to put the metal in the FCAT, we have to find some kind of the optimization condition to make gold deposited on the FCAT. So I'm not sure what kind of metal you want to put, but in our laboratory also use this one to like support other kind of metal like palladium or even copper. But for example, in the copper case, we cannot use pH4 to deposit the copper on the FCAT. We have to use like pH7, pH8 to fully deposit the that metal into the FCAT. So I'm not sure what do you mean by the absorbent, like kind of. I'm not sure. Can you?
Okay. For example, I want to absorb heavy metal, such as what's this?
Like, so in this, I'm not sure if it can absorb or not, but in order to put some kind of metal in the FCAT, we have to find the optimization, and we still found the leaching. So I'm not sure if it the suitable purpose for the FCAT. So maybe no, I guess. But I think everything can possible, right? So it maybe was too high, or I'm not sure.
Okay, maybe it's out of your research. Actually, we have many cellulose biomass consists of cellulose in Indonesia. I think similar with Thailand, I think. So maybe in the future we can develop the use of cellulose in here by using your method. Okay, thank you very much, Ms. Pete. Maybe one question from the audience. Okay, I think the time is over. Thank you very much for your presentations and your research, and good luck. Please give applause to Ms. Pete. And we next move to the last presenter. Last presenter should be Mr. Mamadou Saleh Sowe. He is a doctoral student from our university. He will present about the production of green diesel-rich pentadiene from catalytic hydrodeoxygenation of waste cooking oil using nickel aluminum zirconia and nickel silica zirconia. Are you in here, Mamadou?
Yes, good morning, Boo.
Okay. I think it's very, very morning in your country. I'm sorry.
It is okay. It's a very early morning in the Gambia,
Okay.
but it's fine. Is my slide visible, please?
Yes, we can see it clearly. Yes, time is yours, please.
All right. Good morning, Boo. Good morning to our speakers, and good morning to the rest of the participants, and finally, good morning to my students from the University of the Gambia. It is an early morning actually from the University of the Gambia and from the Gambia by extension. So today I will present on our research which focuses on the production of green diesel-rich pentadiene from catalytic hydrodeoxygenation of waste cooking oil using alumina zirconia, of course, nickel alumina zirconia and nickel silica zirconia catalyst. This is my detail and affiliation. So basically in this research, we intend to synthesize nickel-based catalysts. As you have seen from the title, nickel-based catalyst supported by alumina zirconia and silica zirconia. And above all, subject this nickel-based catalyst to hydrodeoxygenation reaction, which is intended to convert waste cooking oil to biodiesel. While nickel as a metal, because nickel is a very active metal for bond cleavage due to high electron density. And again, basically, so many types of metal-based catalysts have been reported for the purposes of hydrodeoxygenation reaction, supported by all the different types of materials. But oxides are known to have adequate surface area that allows adequate metal deposition on top of them, which makes them a very important support material in metal-based catalysis. Hydrodeoxygenation reaction has the advantage of hydrogenating multiple bond systems and at the same time eliminating oxygen atoms from a compound. And then waste cooking oil, it's a bio-based feedstock that have been used for the purposes of biodiesel or green diesel production via hydrodeoxygenation reaction. So basically in this research, we intend to synthesize nickel-based catalyst, subject the nickel-based catalyst to hydrodeoxygenation reaction for the conversion of waste cooking oil to biodiesel. The nickel catalysts were synthesized by a simple but interesting method, which is the wet impregnation method. We began by basically using some widely available laboratory grade chemicals and reagents for the purposes of the synthesis method. Zirconium autochloride octohydrate was used as the precursor for zirconia. Gamma alumina and silica were also used basically as obtained from the laboratory. So the zirconia autochloride octohydrate basically was mixed in a deionized water. And then the mixture basically, the pH of the mixture was raised to pH 8, and that was observed through the precipitate formation of zirconium hydroxide. So that precipitate basically was respectively mixed with the gamma alumina and also with silica that underwent certain processes, and then that led to the calcination of the mixture to 500 degrees Celsius 5 hours, intended to form a composite mixture of silica zirconia and alumina zirconia. So the respective composite mixtures basically were then mixed with nickel nitrate hexahydrate, and the nickel nitrate hexahydrate was used as the source of nickel metal. The mixtures basically underwent some processes. Due to time, I'm not able to go through all of them. But then the obtained mixtures were dried and then calcined at 500 degrees Celsius for 5 hours to form nickel oxide silica zirconia, nickel oxide alumina zirconia, which was then reduced on the hydrogen gas for 500 degrees Celsius for 5 hours to form our intended catalyst. So in this process, basically, the intention was to generate 15% nickel on top of silica zirconia support and 15% nickel on top of alumina zirconia support. The synthesized catalysts were then subject to characterization, SRF basically to determine the percent nickel loading, SRD to study the crystalline structure, same EDS basically to study the surface morphology, and then to also study the specific surface area of the catalyst. The waste cooking oil, on the other hand, was obtained from the Brawijaya University from a food court on campus. It was not utilized as obtained. The waste cooking oil underwent some pre-treatment methods, and the pre-treatment methods included basically the polarization of the waste cooking oil from this process to this process, and also the removal of suspended solid materials. This is the modified batch reactor that we use for the hydrodeoxygenation reaction. So basically, each of the catalysts was subjected to hydrodeoxygenation reaction of the obtained waste cooking oil from the Brawijaya campus at 350 degrees Celsius for 2 and 4 hours, respectively. That was after characterization. So first, from the SRF results, we, as mentioned earlier on, our intention from the theoretical calculations was to generate 15% nickel on top of the various supports. So for nickel alumina zirconia, we detected instead of 15%, we detected 15.70% nickel content on top of the alumina zirconia support, as shown by the SRF result. On the other hand, we also detected 16.45 instead of 15% for nickel content on the silica zirconia support, as indicated by the SRF analysis. SRD analysis to study the catalyst crystallized structure, we detected the two theta basically angles for nickel at 30 degrees and also 44 degrees and 78 degrees, as you can see here. So basically nickel was detected at different lattice structures. Zirconia, on the other hand, was also detected in two forms, basically the monoclinic form represented as hem here and the tetragonal form represented as T here. For zirconia in the monoclinic form was detected at 50 degrees. Zirconia at the tetragonal phase was detected at 35 degrees, 51 degrees, and 60 degrees in the respective catalyst. This is for nickel alumina zirconia, and this one is for nickel silica zirconia. However, looking at the peaks, SRD peaks for nickel alumina zirconia, the alumina peaks were not detected. All right. Also looking at the peaks for nickel silica zirconia, there was no specific peak detected for silica. So this was suggesting that there was composite formation between silica zirconia and alumina zirconia respectively. This is why peaks were not detected for alumina and silica. So we did FTIR to further determine whether really there was composite formation between our binary oxide supports. And we detected a weak vibration here. Basically, this one, a weak vibration here for nickel alumina zirconia, showing us that there is basically a metal oxygen metal bond in nickel alumina zirconia, and that was suggesting that we basically have alumina oxygen and zirconia framework. And for nickel silica zirconia, we also saw a weak stretching vibration here that was suggesting that there is metal oxygen metal bond. And in this case, for nickel silica zirconia, it was basically for the silica oxygen zirconia framework. So from the FTIR analysis, we were able to confirm that indeed, as intended, there was a composite formation between alumina zirconia and silica zirconia respectively. So from the same EDS analysis, where we are interested to study the surface morphology of our catalyst, the first image here basically is for the nickel alumina zirconia. As you can see here, you see some agglomerations from the image here, which basically based on previous reports, it's been suggested to be caused by the nickel impregnation on the surface of the alumina zirconia support. So for image, the second image is basically the same EDS analysis for nickel silica zirconia. If you also closely observe the image here, you see some agglomerations basically, which is suggesting that nickel basically was successfully impregnated on the surface of silica zirconia. So comparing these two images, you realize that basically on the surface morphology of the two catalysts, there is comparatively smaller particle size for nickel alumina zirconia than nickel silica zirconia. So basically, nickel alumina zirconia exhibited smaller particle size compared to nickel silica zirconia. And this basically is further studied by doing the nitrogen isotope absorption analysis. Our main interest basically is to understand the surface area of our catalyst. Looking at this here, silica basically, if you look at the surface area of silica, before silica zirconia rather, before nickel impregnation, and the surface area from the S-bed analysis of nickel silica zirconia after nickel impregnation, you realize that the surface area of the support, that is silica zirconia, reduced drastically after nickel impregnation. So from 77.59 basically to 17.98. So this is indicating that nickel impregnation on the surface of silica zirconia affected the physical parameters of the binary support. Comparing nickel alumina zirconia and nickel silica zirconia, you realize that nickel alumina zirconia basically exhibited a higher surface area compared to nickel silica zirconia. However, nickel silica zirconia exhibited relatively larger pore volumes than nickel silica zirconia. And when we look at the pore diameter, we realize that nickel alumina zirconia exhibited larger pore diameters than nickel silica zirconia. Basically, the crystalline structure of the two catalysts were studied or were calculated from the SRD data using Serre's equation. And looking at the crystalline sizes, again, we realized that nickel alumina zirconia showed smaller crystal sizes than nickel silica zirconia. So before hydrodeoxygenation reaction, the fatty acid content of the waste cooking oil was determined because we wanted to know what fatty acids are composed in our waste cooking oil. So from GCMS analysis of the waste cooking oil, we realized that octadecanoic acid, specifically 11-octadecanoic acid, is the major free fatty acid content in our waste cooking oil with 75.63%. Even though we definitely have other fatty acid present, but the major fatty acid present in our waste cooking oil is octadecanoic acid. So that was a very good indication to lead us to the hydrodeoxygenation reaction proper. So in the hydrodeoxygenation reaction, as I mentioned earlier, each of the catalysts was tested at different time parameters. We tested each catalyst at 2 hours and 4 hours, but the reaction time was maintained at 350 degrees Celsius under 2 MPa hydrogen gas pressure. So for nickel alumina zirconia at 2 hours, we have basically a variety of hydrocarbon. These are completely deoxygenated hydrocarbons that have been generated. We have C13, C14, C15, C16, and C17, but we have some oxygenated products also generated here, which we will see in the next slide. And again, for nickel alumina zirconia at 4 hours, we have hydrocarbon products, basically complete hydrocarbons compounds are generated, C12, C13, C14, 15, 16, 17, and 18. So basically, we do not have any oxygenated compounds are generated, meaning that the conversion rate was basically 100%, but in this case, the conversion rate was not 100%, as we will see in the subsequent slide. For nickel silica zirconia at 2 hours, we generated basically hydrocarbon chains. These are diesel range hydrocarbon chains from C14, C15, C16, C17, C18. We also basically generated C13 for nickel silica zirconia at 2 hours. So when the reaction time was raised to 4 hours, we also basically generated completely deoxygenated products. These are hydrocarbon compounds within diesel range, the diesel range compound. C13, C14, C15, C16, and C17. So the image you see here basically is the product we generated after the hydrodeoxygenation of the waste cooking oil at 2 and 4 hours respectively for each of the catalysts at 350 degrees Celsius and 20 MPa hydrogen gas pressure. So to understand the influence of reaction time on the variability of the products that are obtained, the waste cooking oil H2O products that are obtained for each of the catalysts, you'll see here for nickel alumina zirconia, the first entry at 2 hours, conversion was not 100%, but very near to 100% because it was just, basically 5% short of 100%. And then we have a variety of hydrocarbon products that have been generated, as we have seen in the previous slides from the GCMS analysis. But when the reaction time was increased to 4 hours, basically conversion increased. We observe 100% conversion and a variety of basically hydrocarbon chains are generated. For nickel silica zirconia, both at 2 and 4 hours, conversion was maximal, was 100%. But we also observe a variety of hydrocarbons generated. The other interesting factor is we are interested in the diesel range hydrocarbons, which is basically C40 to C18. But looking at the product selectivity, we realized that both nickel alumina zirconia and nickel silica zirconia gave higher selectivity for C50, that is pentadecane. At 2 hours, we have about 68%, basically, roughly 69%. At 4 hours, the selectivity decreased a little bit to 58%. For nickel silica zirconia at 2 hours, that is the shorter reaction time, we see 55% selectivity to C15, but when the reaction time was increased basically to 65%, we observed that selectivity to C15 increased. So basically, there are so many factors that we have attributed to some of this that has to do with the nickel content, as we have seen from the SRF analysis, and also basically from the from the same EDS analysis, where we saw the elemental mapping or elemental distribution on the surface of our catalyst, and then the different types of supports. Because if you look at alumina, alumina has specific surface area. From our S-bed analysis, we realized that alumina has higher surface area compared to silica. So all these factors really contributed to the variety of products that we have generated for each of the tested catalysts. So we predicted the pathway that have the pathway undergone by our catalyst for hydrodeoxygenation reaction. From the product variety that we obtained, we realized that basically the pathway followed hydrogenation first. The major pathway followed hydrogenation of our oleic acid, and then which was followed by decarboxylation to give us a C17, and the C17 we suggested that also underwent carbon-carbon or a carbon chain cracking to give us lower molecular weight hydrocarbons. We also suggested a minor route, and the minor route basically is the hydrogenation and the reduction of the oleic acid to give us an alcohol basically, and that alcohol also underwent hydrogenation and deoxygenation to give us a C18, and we suggested that this C18 underwent a demethylation to give us lower molecular weight hydrocarbons. So in conclusion, we concluded that from the analysis of our catalyst, we realized that nickel alumina zirconia and nickel silica zirconia basically exhibited a mesopore type catalyst. This basically is as a result of our study on the nitrogen adsorption analysis. Both catalysts gave green diesel range hydrocarbons, as we have seen, C14 to C18, but highest selectivity basically was maintained for C15. Nickel silica zirconia showed better activity for waste cooking oil conversion. From the previous table, you realize that nickel silica zirconia gave us a maximum conversion both at 2 and 4 hours, but that was not the case for nickel alumina zirconia. But on the other hand, nickel alumina zirconia also gave us higher selectivities for C15 hydrocarbon. So we concluded that both of our catalysts basically have great potentials for the conversion of waste cooking oil to green diesel via hydro basically the oxygenation or hydrodecarboxylation basically, because that is the reaction pathway that has been followed. On that note, I thank you all for your kind attention. This research was conducted in Bu Olfa's lab when I was in Malam. But basically right now I'm in the Gambia, stuck here because of COVID. Hopefully I intend to be in Malam as soon as possible. Terima kasih banyak.
Okay, thank you very much, Mamoudou, for your nice presentation and the nice picture in the last slide, because I'm there.
Thank you, Bu.
Okay, so we now move to the question and answer session. Several questions in chat room. First, I want to read the question from Andrian. Andrian also comes from Brawijaya University in my labs. He wants to ask about what kind of factors that probably increasing the NE. What do you mean, Andrian? Andrian, you hear me?
Yeah.
Maybe
yes. Okay.
Oh yeah.
Okay. Maybe you can directly ask the question to the Mamoudou.
Okay, so Mr. Mamoudou plan to have 15% of nickel in the nickel zirconium, but Mr. Mamoudou got 16%. So what kind of factor that contributing to that increasing number of nickel? Thank you very much.
All right, thank you, Andrea. Actually, we were able to figure that out. So basically, based on reported literature, our prediction was consistent with reported literature. That because if you look at our catalyst synthesis, I will take you to this slide. So basically, if you look at the catalyst synthesis here, each of the support materials were calcinated before nickel impregnation. So the assumption was that there was weight loss during the calcination process before nickel impregnation, and this is why when nickel was impregnated, it somehow influenced the nickel content on the surface of the supports. So that's the suggestion basically. Calcination somehow affected the weight of our support, and that contributed to enhancing the nickel content on the surface of our catalyst.
Thank you very much.
Okay, thank you, Mamadou. And next questions come from Ramadan. Actually, he directly asked to me in Bahasa and want to translate it in English. So it is about the decreasing of surface area of the catalyst after impregnation with nickel. Is it possible to keep the or to increase the surface area by changing the support, for example, changing zirconia into silica or another oxide, metal oxide?
Yeah, basically,
Yes.
each of the oxides have their specific physical chemical properties. So probably, if you play around with the oxides, you might see some changes. There, you might see some influences in the way they behave, corresponding to their properties, basically. So I want to assume probably if you maybe change this silica to one other oxide, you might not observe probably a very big changes in terms of the surface area. You might also observe. It depends on the nature and type of the oxide that you are using. I want to assume.
Okay, is it we can play around with the metal oxide and then check the surface area? And then the last question from me. What do you think about the use of different feedstock for hydrogenation reaction using your catalyst? In here, you use waste cooking oil. Maybe you can suggest another feedstock.
Yes, basically, with regard to the production of green diesel, specifically when it comes to the production of green diesel, so many types of feedstocks have been used. These are bio-based feedstocks, but mostly bio-oils are used for the production of green diesel. So it depends on the type of bio-oil that you want to use. There are so many types of bio-oils you want to use. So there are a lot available. I am sure the catalyst is designed to do hydrogenation and deoxygenation. So long there is a carbon system to hydrogenate, so long there is oxygen to remove, I think the catalyst should be able to be applied for that purpose.
Okay, thank you very much for your response. Because the time is over, and I'm sorry because this is the prolonged long time, I think. Thank you, Mamadou, for the nice presentation. And now we end this session, the student symposium sessions. Thank you for all the participants, all the presenter, also for all the keynote speaker who's still in this room. Thank you very much for all your attention. Please give a big applause to Mamadou. And I deliver this session to the Master of Ceremony. Please, Sania.
Thank you very much, Mrs. Siti Maria Ulfa, Doctor of Science, for the wonderful sessions. It was really interesting that we have a lot of discussions between the speakers. And ladies and gentlemen, if you have any interest on any kind of research that is presented here, whether by the keynote speakers or the students presenter, please do not hesitate to communicate to the RSVP that is already written in the poster so that the committee will help you to communicate to the speakers. And also, I would like to remind you to please fill out the attendance list. That is already the link already written in the chat room so that you can receive the certificate. And also for all the participants who may be late to join today's symposium, I inform you that today's symposium is also live on YouTube and it will be saved so that you can check it on later in the future. And last but not least, I would like to send my gratitude to all of the awesome keynote speakers from Professor Hideki Okamoto, Professor Hidehiro Sakurai, Professor Mikio Nishizawa, Professor Washito. Arigato gozaimasu for the sharing of your research. It was really interesting. And I also want to send my gratitude to all of the student speakers. Andreas Cahyo, Tatsuki Sato, Aoi Tatsuki, Butsaratip Suwatana Nuruk, Mamodo Salusoe, thank you very much for your sharings. And I also want to apologize for any kind of mistakes that maybe I made during the symposium, including misspelling names and misspelling academic title. In the meantime, I would like to thank you for all the participants that already joined today's symposium. On behalf of all the committee, Thanks for your participations. In the meantime, thank you very much. I'm Sani Shaktila. See you next time.
Thank you very much, Sensei.